Good morning, everyone. We're at the 8:30 hour here in the Pacific Northwest. Got about 21 people on this morning. At this point, I suspect we'll have a few more come and join us. So this session this morning will be recorded, and as I'm assuming you're aware, you are joining the Pacific Northwest and Mountain West Nutrient Cycling, Soil Health, and Food Safety Conference. After each presentation this morning, we will take questions and answers live. I would ask that you put the questions into the chat box. And then after all the presentations are done this morning, we will have a 3-question poll that we'll ask the attendees to complete. And then after that's completed, I will put up the QR code if you're wanting to receive continuing education credits for any memberships that you have where that's required. So at this point, I think we'll go ahead and get started. I just shown you a moment ago the agenda that we have for today. Maybe I'll share that quick again. So we're going to have a panel this morning first that'll talk about some different technologies that are out in the field here, and particularly in Washington State. And then we'll move on to a series of presentations from Idaho and other parts of the U.S. So, and an important point this morning to put on your timeline for the morning is we'll take a bio break, a bathroom break at 10:50, so just a little bit before 11. Kind of tried to split the time in half and give everybody a chance to be a little more comfortable. So with that, I think I'll go ahead and start up this first PowerPoint. And let me see here. Just realized that okay. Good morning. Welcome to the Nutrient Cycling, Soil Health, and Food Safety Conference. This is the first talk in the Nutrient Technologies section. I'll be talking about reconnecting the broken nutrient cycle with a specific focus on phosphorus. My name is Joe Harrison. I'm with Washington State University. The project I'll be talking about was a collaborative effort and funded by Natural Resource Conservation Service via Conservation Innovation Grant. We also received support from the Dairy Farmers of Washington and partnered with Multiform Harvest from Seattle, Washington. In this slide, you'll see several pictures. To the left, you'll see a cone-like system that's mounted on a trailer, and that's the system we used for collecting phosphorus from liquid dairy manure at about 30 dairies in eastern and western Washington the last couple of years. The project was to develop a nutrient cycling relationship between dairy producers and alfalfa growers in Washington State. So we worked with the dairy industry to collect struvite, phosphorus in the form of struvite. And then struvite was utilized on 2 different commercial alfalfa hay grower farms, one in Ellensburg, Washington, and the other in Moses Lake. In your lower hand, bottom right, you'll see material that looks much like sand, and that's actually the struvite material that we extract from the liquid manure on the dairy farms. And in the upper right is the application of some of this material to the alfalfa grower fields. So as I mentioned, what we're trying to do is develop a recycling relationship. We know that we move a lot of phosphorus to western Washington via alfalfa, but we don't coincidentally transfer or transport phosphorus to eastern Washington back to where the nutrients are needed. So what we've done is set up a project where we can actually try to build a relationship so that this nutrient recycling relationship can be lasting for decades to come. This slide shows a little bit about phosphorus and utilization by the cow. Only about 27%, or what I do is I round it up to a third. A third or less of the phosphorus that the cow eats actually ends up in the milk carton and shipped off the farm. The remaining phosphorus is in the manure, most of it in the feces, very little of it in the urine. If we look at Whatcom County as an example of a view of reality, in 2002, and this is our northernmost county, we had about 2,362 tons of phosphorus were eaten by cows. About 637 tons of the phosphorus which was consumed was exported in milk. And manure was applied to about 44,425 acres of land. And so that left about 1,724 ton of phosphorus balance, positive balance. So in order to use that, there was really a need for another 44,000 acres. So this back of the envelope calculation really got my attention nearly 2 decades ago. So we've been working over the last 15 years with Dr. Keith Bowers of Multiform Harvest to utilize his technology. It's called a fluidized bed, and that fluidized bed forms in this cone as you see on this trailer. What we do is we use acid to lower the pH of the manure to free up the calcium from the phosphorus, because we need to have the phosphorus in a free form. And then with ammonia and magnesium that are in the manure and attaching to that free phosphorus, then we raise the pH and it makes more of these struvite crystals. And after the system's run for a few days, you can simply shut it down, drain out the bed, let it air dry, and the material is ready to use as a fertilizer source. This is a close-up picture with a quarter as a coin there to give you reference. This is what the material looks like after it's removed from liquid dairy manure. Very easily transported and extremely low moisture. The fertilizer formula for struvite, pure struvite, has an NPK plus magnesium formula of 629.0 and a plus 10. It's a slow release rate of phosphorus, which makes it good for being water soluble and having a sustained release during the growing season, but it's not prone to leaching. So when we evaluated this mobile system across dairies in western and eastern Washington, we looked at reduction of both orthophosphorus as well as total phosphorus. And in 27 runs where we saw a reduction in orthophosphorus being positive, the average reduction was 32%, and the range was 1 to 76%. The very high numbers are a result of manure being digested in anaerobic digesters, and therefore more of the phosphorus in the manure being in inorganic form, which is more available for forming the struvite. In 28 runs where we had total phosphorus reductions which were positive, we had an average of about 29% and a range of 2 to 71.8%. Again, these higher numbers being from anaerobically digested manure. Okay, so we had agronomic use experiments. Again, some pictures from these fields were in eastern Washington, both in Othello and, in Moses Lake and Ellensburg. And we had one field that was a new seeding. There was 64 pounds of phosphorus provided in 2 different forms to the field, split the field in half. One was monoammonium phosphate only, and the other side we had struvite. In the established stand, we, depending on the side of the field, again, we wanted to apply to soil test and also have the same amount of phosphorus there available to the plant. So on the monoammonium phosphate side, we had 57 pounds of monoammonium phosphate, no struvite. And then on the struvite side of the field, we had 48 pounds of phosphorus from struvite and, from MAP, and 174 pounds of struvite to provide this 75 pounds of phosphorus. And then we've looked at this over the last 3 years. So this is data from 2018 and a little bit of 2019. And you can see that on a ton per acre basis, the blue bars are monoammonium phosphate only, and the Struvite Plus MAP are the orange bars. And you see that the yields are very similar. If anything, maybe a slight advantage to the Struvite treatment. This is the second farm. And again, same use of coating here. The orange bars are the Struvite Plus MAP, and the blue bars are the MAP only. Again, emphasize that the same amount of phosphorus was applied to these fields. And we, again, tend to see a little bit of an advantage to the Struvite Plus MAP. This is overall average for the 2 years in both farms. 2019, distinct bit of a yield advantage here with Struvite, whereas in 2018 they were very similar, and that was the initiation year. We just sampled a few weeks ago and kind of finalized our 2020 data, so we won't have all those results for a bit yet. This is pounds per acre of that was actually harvested in the hay over time. Again, you can see a fairly similar performance. In some cases, Struvite provided a little better uptake and removal of phosphorus. So let's talk about the economics a bit. It's common in the dairy industry to talk about what it costs per cow per day. And in this case, what I'm showing you is the chemical costs. So an anaerobically digested manure system was about 22 cents a day to form the Struvite. With a raw manure or undigested manure, it's about 39 cents. But it's really not a very telling number, because what you really need to do is look at what the need is for removal on any given farm. And so you really need to ask the question, how much phosphorus needs to be exported to get balance on that farm? So the net zero balance will be affected by a number of factors, such as number of cows, number of acres utilized for manure application, phosphorus utilization by crops grown, and double or triple cropping practices, diet manipulation, and of course the export of manure off farm. So you can see it gets to be a number of factors considered. So each farm is going to have its own unique solution, and therefore the price per cow per day while it's an indicator, it's not. It's a rough indicator. So what we did is we took some examples. In this case, we had 500 acres of cropland, and the crops took up about 60 pounds of phosphorus uptake over a season, over the growing season, or for the growing year. And we looked at 3 different sizes of herds. So we went from 1,000 lactating cows down to 600. And the cost here then is what it would cost to achieve phosphorus balance given this type of scenario: 500 acres and the respective number of lactating cows. So in each case, it's going to cost you more money to get a phosphorus balance with the raw manure than the anaerobically digested, because again, we can extract more of the phosphorus from anaerobically digested manure. We look at this in a slightly different way. If we now look at the number of acres, but we stay with 1,000 lactating cows, we can see that as we get up here towards 895 acres, it gets to be very little cost to get into a net zero balance for that farm in terms of phosphorus. So it's really critical. Obviously, the cows per acre are a big driver in coming up with these results. So in conclusion, this project demonstrated that phosphorus can be captured from liquid dairy manure under a variety of field conditions. It was most economical when the manure is low in solids, particularly suspended solids and calcium. Then it requires less chemicals to actually perform the process. And also when inorganic phosphorus is a high percentage of the total phosphorus, which would be the case for anaerobically digested manure. The alfalfa growers in the state are willing to use this as an alternative to conventional sources of phosphorus. And so I think we have established a good opportunity here for this to be a success in the future. Thank you for listening, and we'll take questions. Okay, we can take some questions via the chat box there. There was one question came in. And I answered that in the chat box, but I'll go ahead and repeat it. The question was, what acid was used to raise the pH? Well, we use an acid to lower the pH, actually, and the two acids we used were sulfuric or oxalic. And the advantage that oxalic has is it not only lowers the pH, but also binds the calcium, and so it keeps calcium away from phosphorus. So that's an advantage there. And then we raise the pH with either caustic soda or ammonia water. The next question was 39 cents per cow per day for the year, or just the days the system runs. It's really that's what it costs you, for the day that you ran it, and not really prorated out. Each farm's going to have its own unique solution, so that 39 cents per cow per day really is kind of not a really good number. That's why I went into the more advanced discussion about the economics. Their question was, what's the solids percentage before struvite precipitation for raw manure and AD manure? Really like that manure down in the less than 1.5% solids, and the lower in suspended solids, the better, because that does create quite a challenge for forming the struvite crystals and getting them to settle out in that fluidized bed in the cone rather than floating on out through the system. So any other questions from the audience at this point? Okay, I don't see any more coming into the chat box. Okay, one more. Did you try to balance the nutrient content in MAP and struvite treatments? I'm going to restate that. I think what you're asking is, did we apply the same amount of phosphorus to the different parts of the field? And that is correct. That's why we did that. There were equal phosphorus additions. And the other question was, how much volume can you run a day? This particular pilot system on a trailer, and that's kind of the limitation of the volume that could be run per day, because we had this thing on about a 25-foot trailer. We were running at a rate somewhere between 5 to 7 gallons per minute with that. But systems that have been put on dairies in the East Coast, or systems that have been put in wastewater treatment plants, are obviously scaled up where you can go to a lot higher volume than that. So, but in our case, we had it scaled to that so we could move it from farm to farm. Next question was, what did you estimate is available P from struvite for year 1, 2, etc.? One of the techniques that we used was actually a laboratory analysis, is citrate soluble phosphorus, and those numbers, boy, off the top of my head, we're in the 25 to 30% range. And I don't, because we don't have a pure system, it's really hard to say exactly how much phosphorus was available per year from that source. I'd have to go back and try to push the numbers on that. And again, they're going to be estimates, because you've got a huge amount of phosphorus in the soil to begin with. So when you get phosphorus uptake, is it from phosphorus from that year or from a different year? That question can probably be better answered in some controlled plot studies that were done by Steve Norberg out of Prosser, because we actually had check plots there. With these commercial operations, we weren't real interested in asking them to not apply any fertilizer at all to their land. So Trevor, if you want to follow up with me afterwards, we may be able to get you an answer on that. So okay, so I think with that, we'll try to keep ourselves on schedule here. Again, thanks for those very good questions. And our next speaker is going to be Matthias Sojin. And I will start that PowerPoint now. And
Good morning. My name is Matthias Sjögren. I'm CEO and co-founder of Biofiltro. I'm going to explain today how worms They can help cows to cool the planet. Biofiltro is a 4-hour liquid manure treatment process that prevents the formation of methane, and Therby can generate between 6 to 8 tons of carbon credit per cow a year. So most of the farmers, they spread the liquid manure directly into the fields. But we know that liquid manure is very rich in nitrogen, phosphorus, ammonia. The problem is that this land application can burn crops, contaminate ground and water, and require massive amount of land basically to apply all this liquid manure. With Biofiltro, we can remove plus 70% of the phosphorus present in the liquid manure. We can reduce more than 80% of the total nitrogen and plus 90% of the BOD and TSS on the liquid manure in only 4 hours, and so reduce all the land required to do the land application. So basically, our VIDA system can convert nutrients into worm casting, what is a very rich soil amendment with the correct NPK ratio and very rich on aerobic microbes. Our 4-hour treatment process can avoid the lagooning of manure. And thirdly, we can generate the carbon credits associated to the reduction of this methane generation. So basically, the worms, they can convert the waste into casting, which on the low end, we can sell for $65 the cubic yard of unprocessed material. An average dairy cow can generate about 2.25 cubic yard per year of this unprocessed material, worm castings, what means revenues of $150 per year. We have received very positive feedback and comments from different labs that they have analyzed this material and from current customers as well. So we have done also air quality studies, measuring the emissions coming out from the VIDA system in comparison with the emission coming out from a conventional liquid manure lagoon. In summary, the Biofiltro can reduce in 97 to 100% the methane generation from a conventional lagoon. We can reduce between 60 to 85% of the emissions coming out from this lagoon as carbon dioxide. And as well, we can reduce practically 100% of the ammonia present in the liquid manure. Once the Biofiltro system is installed, it can provide a positive cash flow for the dairy in an annual basis. What that means is that the revenues coming out from the castings and the carbon credits are higher than the cost to operate the system. So in a conventional dairy of 3,000 herd size, we can provide a positive cash flow for the dairy farmer of $30 per cow a year. We have implemented a successful 500,000 gallons a day treatment system at Royal Dairy in Eastern Washington. The system is avoiding the equivalent to 42,000 metric tons of CO2 every year, and also enable the dairy to reduce their land application needs area by 90%. Well, I want to thank you to give us the opportunity to be present in this conference. Thank you very much and have everyone a great day.
Okay, so let's move to the questions here. And we have plenty of time for questions, so I'm guessing the audience will have quite a few. So Matthias, the first question is, how does the system work during the winter or the colder months? And what was
Good morning, everyone.
what was cold? You know, what were the temperatures?
Yes. So, good morning, everyone. The worms basically we use like a 3 to 4 feet wood shavings and wood chip media. So in general, in the summer, the worms they live in the first feet in the top layer, and during the winter they go deeper. There is always a reaction happening inside this beta system. So they found the temperature inside. What we need to take care more than the worms is that we don't freeze all the pipes that irrigate the biofilter system. So we have like a recirculation system that we keep water moving all the time to avoid freezing inside.
Okay, so kind of tied in with that, let me see here. Let's just jumped a little bit. How is the worm efficiency dictated by climate? So as you have warmer and colder temperatures, how does efficiency work? Do you see differences in nitrogen removal and so forth?
Yeah, we have done studies for more than 2 complete years in dairies in California, in Washington. We have system in very cold areas. We have a system running for domestic sewage treatment in the Antarctica. And basically the efficiency in terms of nitrification and denitrification during the year is pretty stable. We have averaged over 90% total nitrogen removal on the dairy in Washington. So we don't have any information that says that it's gonna decrease the reduction during the cold month.
Okay, and then what kind of dairy waste system works best? And this is really targeted towards, for example, flushed manure versus say scraped manure, or
yeah. What we have done, at least in the Washington dairy, is that we are treating by the Vida system 100% of the flash water coming out from the first screen. So, and all the treated water after the Vida is the water we reuse to flush the dairy back. So instead of flush the dairy with manure, we are flushing the dairy with Vida treated water that is 95% cleaner than the liquid manure. And that's not only improve the whole water quality, but improve the whole environment of the dairy, improve the health of the cows, improve all the odors. We don't have more manure ponds, and we have just a treated water pond that doesn't emit any methane. So we can do both. We can do scrape dairies also. It's going to be a smaller system because most of the manure is scrape. So you basically treat only the wastewater generating the milk parlor. But in the case of a flush dairy, flush the dairy back with treated water of the Vida, I think is the best way to go.
okay, and is there a rough size or acreage of area needed per 100 cows of treatment? So for the Vida system.
Yeah, so if it's a flush dairy, we need about 70 square feet per cow, per milking cow. If it's a scrape dairy, this number go down to levels of 20, 25. So depending of how the dairy operate, if it's a flush or a scrape, it's gonna move anything between 20 to 70 square feet per milking cow a day.
Okay. And I think that kind of answers the next question, which is how many acres are needed for a system of 1,000 milk cows. So I think you've kind of provided the basis for doing those calculations. Yeah.
Yeah. So if it's a flush dairy, 1,000 cows, we're gonna need 70,000 square feet, what is about 1.5 acres approx.
Okay. And then how often do you remove the bedding or harvesting of the worms? So bedding being your, really your material inside the.
Yeah. So in the dairy, in general, we change the material every 18 months. We start with 3.5 feet of wood chips, and after 18 months, all these wood chips are transformed into worm casting, and we harvest like 2 feet high of worm casting. We take it out and we replace with new wood chips, and we only seed the system back with 10% of the worms we remove. So all the material we remove basically is very high, or it's worm casting with a very high density of worms. And this material in general we dry for 6 months, and after that you have a great product. You can screen, you can bag, but it's a very rich soil amendment.
And then the HRT, or the retention time, what kind of
Yeah, it's gonna depend how dirty is the water, how they run the dairy. We have done anything between 0.5 to 2 gallons per square foot a day, depending of how dirty is the water. The main design factor here is the total suspended solid. We can apply 0.06 pounds of total suspended solid per square foot of system per day. That's the main design parameter. So depending of, I have seen liquid manure effluent from 1% of suspended solid to 3% of suspended solid. So it's gonna depend of how dirty is the liquid manure.
Okay. Return on investment, what kind of a time frame are you thinking that might be involved with this system?
Yeah, well, it's not an easy to answer, but basically right now, if a dairy is applying the liquid manure in the land and doesn't have any cost to dispose, is not going to be a return over the investment. Wastewater treatment is always a cost. So there is return of investment for the dairies that they don't have land to apply all the nutrient they generate, or all the dairies that they are tracking liquid manure. All of those are really candidate for the biofilter system. But if you have all your land available and you are complying your nutrient management program, it's very difficult to get a return over the investment.
Okay, and then with regard,
unless the price of the carbon credit in the future goes up considerably, but right now with $4 a ton, it's difficult.
So with regard to the actual setup of the system, I think you mentioned that the system was about 4 feet deep. So, what are the different layers that are in the system in terms of materials?
Yeah, so this is a 4.5 feet high pool that can be above ground or over ground. And we have in the bottom, it's a liner. Basically, they recollect all the percolation water in the bottom. Over this liner, we have a plastic pallet. Over the plastic pallet, we have 1 feet of rocks, crushed stone, like 2-inch size. And over that, we have a mix of wood chips and wood shavings, about 3 feet high. And over that, we have all our irrigation system that sprinkle the water in the bed, and the water, it percolate all this layer. It take about 4 hours to percolate down until the water is recollected in the bottom. That's why the retention time in the system is around 4 hours.
Okay. And then I know a question that I had that came up a week ago in another conference that I was in was the nitrogen. There's a quite a large reduction in the nitrogen from the input to the output of your system. What form of nitrogen do you think that is getting transformed and then emitted from the biofilter system?
Yeah, so we nitrify practically over 95%. So we nitrify practically all the ammonia in the liquid manure. In the liquid manure, basically most of the nitrogen is in ammonia stage. So we nitrify all this ammonia, and the denitrification of the system is not complete. So most of these nitrates that we have, or 50% of those are gonna transform into nitrogen gas. Another 50% are gonna stay in the wastewater. But the good thing is that at least you get a water with no ammonia and with nitrates. That is basically, the state of nitrogen that the plants want,
Okay, so primarily nitrogen gas then in terms of what would come off the top of the system. Okay.
Yeah.
And then another question that came in, do you recover the worms when harvesting for reuse or for commercialization?
We recollect about 10% of the worms that we remove, and the other 90% it stay with the material we remove. The material we remove it's not mature, so we need the worms continue working there to have a complete mature process that basically is break down all the carbon into the nutrients. So what's happened is that these worms, they stay in the piles of the castings, they start eating, they continue eating, and after the food is enough, you lose practically a lot of worms. But when you screen this material, let's say to put the fine material in a bag, you recover part of this worm in a trommel screen. So all this worm come back to the system. But right now, no, we are not recollecting 100% of the worms because we don't know neither that it's a very big, industrial market for those. There is some people selling worms, to create like small worm farms in the houses, but the amount of worm we generate is huge. So at least now we don't see a market for those.
Okay, and we've got a couple more minutes left here, so maybe a couple questions I have. In terms of the worm castings themselves, so what kind of nutritive value and what are the primary markets that might use these?
Yeah, so the value of the worm casting, we have 2.5% nitrogen. We have good rates of nutrients, but the most value of the worm casting is the aerobic microbes we have inside. It's like more than 10 million more than in the compost. And you find also about 2.5% of humic acid and fulvic acid. So it's a product that most of the, let's say, the cannabis industry, they love it. Some of the organic vineyards, they love it. So everyone that produce organic products, they love the worm casting. And some of them, they like to mix, let's say, 10% of worm casting with 90% of compost or other kind of fungi. So there is some people doing some blending also, but I will say the more valuable part of the worm casting is the aerobic microbe density we develop inside.
Okay, well, thank you, Matthias. Lots of interest there, and I'm on the graduate committee of the student that's been working at that site, so it's been interesting me being a part of that and listening to the progress there. So looks promising. Okay. Now we're going to move on to our third presentation for today, and that's by Eric Powell from Regenus. And I'll go ahead and boot up his video presentation.
My name is Eric Powell. I'm Director of Business Development for Regenus, and I'll be sharing with you an overview of sequential treatment of dairy manure. The goal of this presentation is to share with you an overview of key separation and treatment technologies that we here at Regenus have installed and operated on dairy farms over the years. A lot of our experience is with dairy farms that have anaerobic digesters, so a lot of it will be post-digestion treatment, though some will be treatment on facilities that do not have a digester. So to start off, generally speaking, we believe in a sequential approach to manure treatment. Again, a lot of our experience is with anaerobic digestion or post-digestion treatment, though an anaerobic digester is not necessary for treating manure in an advanced way or any of these ways that are highlighted here. Most of our experience is with a primary solid separation step, advanced solids separation step, and then clean water generation. So in terms of primary separation, this is something that's happening on a lot of different farms. Won't spend a ton of time on it, but it's something that can be done with a screen or a screw press. And again, is very common with the goal of removing those bulk solids and keeping them out of a lagoon. because you don't want to have to clean lagoons out. So again, very common. And after the primary solid separation step, some farms are choosing to do an advanced solid separation step. A lot of different techniques there. You can use a centrifuge, belt press, dissolved air flotation, or DAF. You can add polymer to get more solids removal. Most of our experience is with dissolved air flotation systems, which was what I'll be talking about more. But in that step, you're concentrating a lot of the phosphorus and nitrogen nutrients in those solids. The tea water that comes off the fine solid separation step can be further concentrated or treated. Most of our experience is taking that tea water and sending it through membranes to generate clean water and concentrate. Primary solid separation step, again, very common. Goal is to keep solids out of lagoons so that they do not have to be cleaned out, and after being filled with solids, they can be used for liquid storage for the farm. The cow generates about 10 yards of this per year. It's a dry-ish product that can be stacked. The thing that we like to highlight here, or I'd like to highlight with this presentation, is that while this is not a new technology and it is being widely used, a market for the product, which is these solids, has taken a lot of time to develop. A lot of people have spent a lot of time and energy into developing a market for these solids. And it is something that some have been able to capture some value for. But when we're talking about more advanced manure treatment steps further along down the line here, something to keep in mind is that markets for these products or byproducts is not something that is very easily put together, or value for these products is not always realized in a timely manner. So it does take time to build markets and make the products into something that can be used. So fine solid separation step, as you can see here from the picture A, it looks a little more advanced than it is. Each step in the sequence gets more and more costly. But with the fine solid separation step, we generate about 5 wet tons of solids per cow per year. They are stackable solids, but they do have more of a clay-like feel to them. And there's a presence of some polymer, because the way that we get these solids out of the manure is we take the effluent off the primary separator, goes to a buffer tank, and then is pumped to the dissolved air flotation unit, where it's mixed with air and polymer solution. So the polymer binds the solids together. They're bound together around those air bubbles that are being injected into the influent to the DAF. And once they go into the tank that you see there in picture A, the solids float and are skimmed off the top into a dewatering step where moisture is removed, and you get the stackable pile that you see in picture B. That picture B there is about a day of production for 1,800 cows. So as you can see, it adds up to a significant amount of solids that then have to have a home, but they are concentrated in nutrients. About 80% of the total phosphorus and 30% of the nitrogen ends up in that pile. And you can see from the graph there that it's been well documented that the nutrients stay mostly with those solids. So there's a lot of correlation to those solids and containing a lot of the nutrients, but it is added O&M costs and added complexity in order to get that nutrient concentration. Not going to spend a ton of time on this slide, but as you can see, there's some data here showing fibrous solids, fine solids, and tea water liquid and their makeup. That can be reviewed at a later time when this presentation becomes available. You can see what each one of those products looks like. For a more visual representation of that, we've got this slide here, where the jar in the top left is raw manure. As you can see, though the picture is a little blurry, you can see that there's a lot of solids in there. That's manure coming, right into the pit at the farm. In this case, the second jar is effluent from a digester prior to separation. So with the colored bubbles, you'll see that there is some significant reduction in solids where those solids were used to make gas. But virtually no impact on the nutrients that's in the manure. So after digestion, there's primary separation, where we do, again, remove a significant amount of solids. And then we start to see some removal or concentration in the nutrients in the liquid after primary separation. But really the biggest jump is from the primary separation to the effluent of the fine solid separation, where again, there's a significant reduction in solids, and this time it correlates to a much more significant reduction in nutrients, particularly phosphorus and nitrogen. And that concentration is now in those fine solids. So there it can be more easily or precisely applied, but they do need to be either applied to fields far away or need to be handled in some way because they do contain a bulk of the nutrients. I'll also point out that if you look at the jars, the liquid being poured out of the jars, if you look at the one on the far left and compare it to the one on the far right, which is raw manure to tea water coming out of the dissolved air flotation unit, there's a significant reduction in viscosity, making that liquid considerably more easy to handle. Obviously, there's less solids in it, so solids buildup in the lagoon becomes less of a concern. So after fine solid separation, you can further treat the manure. What we have the most experience with, again, is membrane treatment to generate concentrated nutrients and clean water. Our experience with membrane treatment is actually on a farm that does not have a digester. What we see at that facility is that manure is sent to a screw press for primary separation where the bulk of the solids are removed. There's a buffer tank that is used to continuously feed the fine solids separation system. In this case, it's a polymer flocculation system to remove the fine solids. I'll point out that there's lots of different fine solids removal approaches that could be put in this place, and a combination of fine solids removal approaches could be put here, such as centrifuge and DAF, just DAF, centrifuge with polymer. Just depending on what the waste stream is and what it looks like, you could use a variety of approaches there. But the big thing is you just got to remove all of the suspended solids prior to sending that liquid tea water to the membranes. With the membranes, you'll have a concentrated liquid containing a lot of the nutrients or all the remaining nutrients, and a clean water that could be dischargeable or used on farm for cow drinking water, or has a variety of uses and benefits. Another more visual slide here where you see manure. In this case, it's post-primary separated liquid manure. And then the next jar, you see that same manure, but after polymer has been added to get the solids to flocculate. So you've got the flocculated solids on top, the tea water on the bottom. That tea water then is sent to the reverse osmosis membranes where we get concentrate and clean water. So if you're looking at the percentages of where these different byproducts are, you've got 24% of the volume ends up in the solids, 33% in the concentrate, and 43% as clean water. If you look at it from a standpoint of after the fine solid separation, that's a 60-40 split between clean water and concentrate. If you look at the data down below here, you'll see some information on the concentrate and the clean water. I'll let you look at that on your own. I won't go through that, but what you'll find is that the clean water is very clean, in most cases dischargeable, and the concentrate does contain pretty well concentrated nutrients, particularly nitrogen, that can be more precisely applied and in a volume that's greatly reduced when it comes to something like having to truck it a long ways. Some of the economics of these systems are displayed in this slide here. Again, our steps are fiber separation, fine solid separation, and then clean water. In this case, we're assuming that a digester is in place ahead of this because that's what most of our experience is with. So you can see that for each step, there is capital and O&M cost. In each step, those capital and O&M costs are increasing. So it costs more and more to get the last little bit of concentration or nutrients out. Like most things in life, the first 90% is pretty easy and the last 10% can be very difficult. So as we treat things more intensively, but obviously the costs are going to go up. Some considerations when looking at manure concentration, manure treatment are what level of post-digestion or what level of treatment is necessary. How is somebody going to afford it? What are the technologies? How do you make it pencil? You know, each farm is different, so not all farms need to go all the way to clean water. That's why we believe in a sequential approach where you add what you need, and then if that need changes as you go on, you add an additional technology that's complementary and not, you know, totally start over. To be able to afford it, you know, milk prices are not super high right now, so the farmer has to think creatively on ways to be able to afford technologies like this. There's lots of different technology providers that provide technologies that do slightly different things and have benefits for different farms. So a farmer should look at all available technologies, you know, including ones that I'm not presenting on here, but others will, to see what's the best fit for them. Proforma's consideration needs to be, is the co-products going to have any value? If the co-products have value, is it something that is desirable by the market as it is, or does it need to be further treated to be desirable? You have to start thinking about things like offset costs, lower trucking, maybe just staying in business. So there's lots to consider when doing a pro forma, and it's not going to look like your traditional, for example, digester pro forma, or it's going to be a little bit hard to factor in. I'll point out also that there's a lot of emerging technologies when it comes to nutrient recovery and nutrient concentration, and it's definitely something to keep an eye on, as there are a lot of approaches that show promise and could be, you know, something that is a consideration in the future. So environmental pressure on dairies is going to continue and is likely to expand. So this is something that, you know, dairies need to be educated on, regardless of the approach. A lot of these different treatment processes are coming from the municipal sector and need to be augmented or adjusted and modified to be used at dairy. Dairy manure is different, and so the treatment of it is going to be a little bit different than what we see in the municipal sector. And it's going to be costly. Like I said before, the first 90% of anything in life is pretty easy, and it's the last 10% that really gets hard and costs money. So, you know, there needs to be some state, national assistance, perhaps creative business plans, or maybe even integrate them with renewable energy projects where, you know, some revenues from one thing can offset some advanced treatment costs. That's all I have, and I look forward to answering any questions that come up. Thank you for having me.
Okay. Well, thanks, Eric. You can go ahead and unmute because we do have at least one question coming in here. So the first question we have is, what size farm would the sequential system become economically feasible?
So that's a great question. And it depends on which step you're looking at. And it also depends, I would say, this is one instance where not necessarily the size of the farm, but just some of the circumstances surrounding the farm come into play. For example, if you have a land base that's not very close to your farm and you need to truck nutrients a long distance, for example, then it might make sense to, you know, pay to treat it further to concentrate some nutrients so that you can truck something that's more concentrated, be it DAF solids or concentrate from a clean water system. What we are seeing is that, you know, it's not always the case here that a bigger farm makes this more easily pencil than say a smaller farm. It more, again, depends on the circumstances around the farm and what they need to do in order to apply their nutrients, or what kind of environmental pressures are in their area.
Okay. Any other questions from the audience? I'll ask one while we're waiting for additional things to come into the chat box. One of the things I've seen in the popular press over the last decade, and some of these have come out of the Midwest, is the concept of producing clean water for so that it actually could be discharged. What do you think the opportunities are there, and feasibility of that?
Yeah, I think that depending on your location, it is absolutely feasible. We have a little experience with a pilot scale project that we're working on here up in the Northwest Washington state. And, when say a municipal plant goes to discharge their effluent from the plant, there's some benefit that you get from like a mixing analysis where, you don't have to necessarily meet all the requirements for whichever body of water you're discharging to right out of the pipe, depending on the flow of, say, the river, and some, whatever, constituents are, of importance there. You get some benefit of, say, like a mixing zone, so you could take your sample and within 10 feet or 20 feet or something like that. So depending on what you have around you that you are able to discharge to, I think it's absolutely feasible. But again, if you have a very small ditch where it's basically going to be the water coming right out of the pipe, you might need to treat it a little bit more, in the case where we're talking about reverse osmosis membranes from dairy manure, it might be slightly over the ammonia limit just on its own. That might be the one thing that you'd have to treat a little bit for, depending on what the requirements are of your body of water that you would be going to.
Okay. Well, I haven't seen any other questions come in, so I think at this point we'll go ahead and close off for your session. But thanks for being with us today and providing that comprehensive look at treating manure.
You're welcome. Thank you for having me.
Yep. Okay. So just to keep us on time, because I do know that some people are going back and forth between sessions. My clock says we're about 9:27, so I think I'm going to give us a couple minutes before we start this next presentation. So if anybody wants to take a quick bio break or grab a cup of coffee, feel free to do so, and we'll start up in about 2 minutes.
Going to be presenting flash dairy manure, nutrient and solid particle distributions with two co-authors, Kevin Kruger and Howard Nibley. All of us from the Department of Soil and Water Systems, University of Idaho. For today's presentation, I will give you a brief project background information and what we did, what we have found. So first, project background information. Idaho has a strong dairy industry and ranks among the nation's top 5 milk producing states. In 2019, Idaho had roughly 437 dairies with about 586,000 milk cows. Average cows per dairy in Magic Valley, southern Idaho were about 1,400. Large dairies often use liquid manure handling system because of their easy of mechanization and low labor requirement. Some of Magic Valley dairies use a flushing system that result in large amounts of liquid manure applied an irrigation system to adjacent cropland during growing season. I'll give you an example for 4,000 milk cows that have a 16 feeding alley. They flush their manure land 3 times per day. Each land need roughly 10,000 gallons. So together, about 500,000 gallon liquid water generated on this dairy. Of course, they will reuse their flushing water. So solids and nutrients present in the liquid manure pose several challenges to manure handling processes. So liquid manure with high solids content flows into a storage lagoon where some of the solids settle to the bottom of the lagoon, resulting in reduced lagoon capacity. Eventually, the solids at the bottom of the lagoon need to be removed to increase the capacity, which is a costly financial burden for dairy producers. Cleaning a lagoon will cost roughly 1 penny per gallon capacity. For example, 10 million gallon lagoon will cost $100,000 each time. So liquid manure with high nutrients, especially phosphorus, limits the land application rate, which means larger areas are needed to apply the same amount of liquid manure. This results in transporting large volume of liquid manure longer distance, which is not cost effective either. Normally, if hauling the liquid manure more than 3 miles will cost extra 1 penny per gallon. That's a lot of money. Liquid manure with high solid has a higher potential to plug pumps, transfer pipes, and the sprinkler nozzles. It requires more power to pump the same volume and requires higher pressure at the pump, thus increasing the risk of rupture seals and manure spills. Liquid manure with high solids could seal surface of croplands, preventing water from penetrating into soils. So separating more solid and nutrient from liquid stream reduces overall manure handling costs. Identify liquid manure solid particle distribution and associated nutrient helps choose suitable separating technologies and equipment and make better manure nutrient management practice. So here's what we did. We went to 3 commercial dairies. We call Dairy SF, Dairy DD, and Dairy SE in Magic Valley, southern Idaho to collect liquid manure from flush and receiving pit on each of the 3 dairies. Each sampling consisted of removing 5 gallons of liquid manure from the receiving pit. The manure samples were then transported to the Waste Management Laboratory at the University of Idaho Twin Falls Research and Extension Center. Triplicate samples were analyzed for solid content, particle density, particle size distribution, total nitrogen, and total phosphorus in the raw manure, and associated with each particle group. The solid content were analyzed using a standard method used by a dry oven. So the nominal pans were placed in an oven at 105 degrees C for 24 hours. And we waited before and after the weight and calculated the solid content. Particle size distribution was determined using a set of 6 8-inch stainless steel wire sieves. The pore size was 4, 2, 0.5, 0.25, 0.125, and 0.063 millimeter, combined with a hydrometer method for particle size less than 63 micrometer. I want to mention the hydrometer method and the standard pipe method we use for analyze the nutrients require that 90% of the manure solid be smaller than 75 micrometer to perform the test. That's why we included sieves with pore size down to 63 micrometer. This is a saved particles in the sieve and the dry that we put in the bag. Particle density will analyze using pycnometer with methanol medium for particle size of the 4 to half, a quarter, and a 0.1 to 5, 0.063 from the 6 sieves. And all the particle less than 63 micrometer were put together as a group. The pipette method was used in conjunction with the hydrometer method to extract liquid manure sample for analyzing total nitrogen, total phosphorus. The hydrometer method runs from 2 minutes, 15, 16 to 150, the 40, 140, and 2 days. At each time point, we'll get a liquid, use a pipette method out, and at the same time, we'll get a hydrometer meter reading. Then based on standard method, we can calculate the particle size and use Hex spectral photometer to test the sample manure from 1 liter cylinder, get a T and a TP associated with each particle group less than 63 micrometer. The table 1 shows total solids, total nitrogen, and total phosphorus concentration in liquid dairy manure samples collected from the 3 commercial dairies. We can see the total solids, the total nitrogen, total phosphorus vary from dairy. That's because their manure handling method a little different and maybe use different flushing water. Even when you went to dairy the morning or afternoon, you will get different manure. And we hear total solid range from 1.8% to 4.3%, sorry, for the 3 dairies, and the total nitrogen range from 0.12% to 0.17%. The TP have a lower value that ranges from 0.04% to 0.06%. This is a flushing dairy manure solid particle density of dairies SF, DD, and SE. The particle density of 3 dairy were found to be similar, ranging from 1.32 gram per cubic centimeter for the particle sizes larger than 4 millimeter to 2.2 gram per cubic centimeter for particle less than 63 micrometers. The particle density was smaller than commonly used soil particle density of 2.65 gram per cubic centimeter due to bedding material of organic matter. In Magic Valley, the Southern Ida, almost our dairy use a compost nature as their bedding material. No sand bedding was used. So flushing dairy water settling basin design based on particle density of the soil particle, the 2.65 gram per cubic centimeter will not work well in terms of settling organic particles due to their much lower particle density. This flush dairy manure solid particle distribution of from the 3 different dairies. It was noticed that higher bedding fiber will present in the liquid manure from dairy DD, which result in a higher percent of roughly 33% of solids with a particle size larger than 4 millimeter compared with just 8% or 17% the same size from other 2 dairies. But most mesh sizes primary inclined screen used on Attica dairy were larger than 0.5 millimeter. So the percentage of solids with particle size larger than 0.5 millimeter were 21, 49, and 33% of for the dairy SF, DD and SC respectively. So if we put the three larger particles together, we get this number. So that said, use a primer screen, inclined screen with pore size larger than 0.5 millimeter. At most, you can get 49% of solid out of your liquid manure. It's the total nitrogen associated with each particle diameter group in the flash and liquid dairy manure. Again, if we add the 4, 2, and 0.5 particle group together, they were about 34%, 44%, and 7% of total nitrogen associated with a particle larger than 0.5 millimeter in the flash manure from the three dairies respectively. It's the total phosphorus associated with each particle diameter group. So there were about 14%, 23%, and 14% of total phosphorus associated with a particle larger than 0.5 millimeter of the flash manure from the dairy SF, dairy DD, and dairy SE respectively. Clearly, we can see most of TP were attached to the fine particle with size less than 0.5 millimeter for the three dairies. But in order to separate more TP out of the liquid manure, definitely advanced separation method or equipment beyond the inclined screens are needed. So take-home message, flash dairy manure particle density range from 1.32 gram per cubic centimeter to 2.2 gram per cubic centimeter. The percentage of solid with particle size larger than 0.5 millimeter were 21, 49, and 33% for dairies, SF, DD, and SE respectively. Most TP were associated with a fine particle size less than 0.5 millimeter that cannot be screened out by screens. Advanced separation technology are needed to capture more TP from flash and liquid dairy manure. This study was supported by USDA and IFA West and Sarah funds. So any questions, comments, or suggestions, please contact me either via email at lchin@uidec.edu or call me at 208-736-3615. Well, thank you for your time and attention. Well, take care. Bye-bye.
Okay, we'll open up the questions now. So Leedy, are you? Yeah, okay, yep, there you are.
Yep.
Great. So anyone would like to post some questions here? So Leedy, as a part of that, did you work at different parts of the year on these dairies, and did you see anything that you would, so what kind of variability over time, temporally, did you see?
Yes, there. You mean the solid minute in the flash liquid manure, right?
Yeah.
For this specific case study, I think we collect manure within a pretty short time, maybe three months. But we have other research during the whole year. We noticed that, yes.
So what kind of variability? You seeing like a 50% variation, 100%? What kind of variability over the season of the year would you see, you think is reasonable?
So exact number, I don't remember. I will see probably on the same dairy, there are no 100% like that, but different dairy, yes, they're different. Some dairy we noted they're even less than 1% solid, but some over 3%. But on the same dairy, I don't think there's so much difference.
Okay.
In the different months.
We saw more seasonal variation between winter months and summer months. We would see a little bit thicker manure in the winter time, and then as it warmed up, we would see, less viscous manure, and that would provide a lot of the variation.
Okay.
Yeah, by the way, Kevin is a technician, make all things work. He went there, collect manure samples.
Yeah.
Thank you, Kevin.
One of the questions came in, is there any relationship with type of bedding material and feed with the particle size diameter? So,
to my knowledge, all the Magic Valley there use compost as their bedding material. I didn't check with them. I don't know whether their feed is different. I guess they're probably a little different. But from the test result from the three data, I don't think their feed much different. But we do notice that they flush their manure nets, maybe use a different amount of water. See, some there maybe just use 10,000 gallons. Some maybe use a little more nets. That's resulting much different sonic percent. And also when we collect manure, maybe sometimes we notice their undigested fiber. Maybe when we go there, we disturb the cows. They're more active, get some bedding manure to the flush manure. We didn't take that longer fiber out of the liquid manure. So that made some difference. I think if we take care of, we get all the longer fiber out, there should be less difference among the three dairies.
another question that came in is, did the recycled flush water affect the solids content after each flush?
I guess yes, definitely. See, when I talk with a dairyman, a lot of their use a centrifuge. They reuse their flushing water. So once they reuse their flush water and centrifuge, they kind of change the solid distribution. They may also affect their screen work. So that way, I think they affect their solid in the liquid manure. Yes, with and without reusing the flushing water.
Okay. So another part of that is so how clean was the recycled flush? So how much did that contribute to particle size? Was the recycled flush fairly clean, or did it actually have its own contribution of solids?
I don't know how to identify the clean, but definitely looks still dark to me. That reusing flushing water, you will add more the finer particles. Definitely the screen green will get out the longer undigested fiber out of the liquid, but they leave the finer particles still in the water. So that will add on and on.
Yeah, so I have something to add. So it's not shown here, but sometimes when we would look at like dissolved solids, sometimes we would see more dissolved solids in the system afterward. And I mean, when you're looking at variation, yes, I mean, it is problematic.
Okay. Then one methods question. This had to do with how you dried your samples. You had air drying versus, well, they asked if you had air drying versus oven drying, would you get any transformation of nutrients from the organic to inorganic form?
I think we only use oven drying. We didn't use air drying for this test data.
Yeah.
Yeah, we didn't.
Okay. All right. Okay. Well, thanks for being with us this morning and answering questions. And go ahead and move on to our next presentation. There's another solids and nutrient removal system. We're looking at pole plug sedimentation basins by Tim Cantor. And we'll pull that up now.
Good morning. My name is Tim Cantor, and I'm here to talk about the pole plug sedimentation basin for medium and small scale flush dairies. Before we get going, we need to thank USDA NEFA for funding the project, or at least part of the project, through the management of nutrients for reuse or manure, a larger grant that we're working on. Also like to thank Tang and Joe from the University of Missouri, Rick Stowell from the University of Nebraska, and Troy Chalkley from the USDA NRCS. So always good form to talk about what you're going to talk about before you talk about it. The PPSB introduction is going to kick us off, and we're going to get into the size, what this thing is, how it operates, etc. And that's going to fold right into the performance and what we've seen within or among various operations of the system. Get into some insight into what other people are saying for similar systems or what can be expected there, and then next steps and future research to wrap things up. So the PPSB is essentially a sedimentation basin. It is a liquid solids separation device. It's a sedimentation basin with a bit of a twist on it, and it can probably best be related to a weeping wall in terms of both cost, I think, as well as performance. This is relatively a new development, a new technology. There's only about 6 installations in Missouri, and the USDA has claimed that among those 6 installations, they're seeing about a 90% solids retention, which I think is approximately where weeping walls are. We got involved earlier this year, maybe 6-8 months ago. We haven't been working on it too terribly long. These installations have been designed, I wouldn't call it trial and error, but this seems to work sort of process. And so we wanted to collect some empirical data, begin to put that together so that these could be scaled smaller or larger in the future. These have been applied to dairies or flush dairies with herd sizes between 120 to 160, maybe as high as 180, but a pretty tight herd size. And there's quite a few of those, I think, around the state of Missouri and probably throughout the country. We've got 2 data points on the cost of this. One, the $26,000 was a pre-construction estimate from USDA, and that seems a little bit low. We've gotten another from a producer, a farmer, that said it was $60,000 for him to build the PPSB and adjoining sand lane. So he was unable to split those out, I think, from these, and we'll go along and continue to collect data points on cost. But I think that it can probably be expected to be somewhere between $35,000 and $45,000 for the PPSB alone. Now that figure, that number is surely going to change and will probably be variable depending upon location in the country, the topography of the surrounding area, as well as the geology of the land involved and what has to be done in order to actually install this, of course. The dimensions of the PPSB have been relatively consistent for these 120 to 160 head. The most important design parameter, we believe, is the depth. The curb to floor height of 6 feet has been chosen and has been applied, I think, to all. It's 1 foot to 1.5 foot of freeboard, so a minimum operating depth of 4.5 feet, I think ideally 5 feet. And the reason that's needed is to allow solids to both settle as well as to provide some ability for the mat to form. The idea is that there's a floating mat that forms on top from undigested fiber or fiber bedding, and then water is then filtered through that mat as it forms, very similar to the weeping wall. Now, the 20 by 20 length and width of the flat floor as seen below is strictly a solid storage, solid capacity thing. They target having to clean this thing out every 3 to 4 months, but it varies greatly depending on rations and the type of bedding used. The ramp that leads down to that flat floor is based on that 6 foot and applying a 12-to-1 slope to it. I know it says 5 degrees here, it's really like 4.76, but the 12-to-1 was seen as the maximum slope possible to minimize cost while also allowing for a skid steer loader to get down there and safely remove bedding from down below. The quote unquote pull plug, which is really this twist on the sedimentation basin, it has been a 6-inch diameter, typically PVC pipe that fits into a slip joint at the bottom of the basin. That is pulled when the basin becomes full. The basin is full when the settled solids on the bottom meet the layer of floating solids on the top, and that interface is formed, at which point that plug is pulled, allowing any additional water to drain from the basin. That whole plug is surrounded by a 12-inch diameter pipe, perforated, that acts as a baffle to allow that mat to form versus being flushed down the drain. That pipe, that baffle, extends up to the curb height and then drops anywhere from 1.5 feet to 2 feet below the operational water surface. This can be arranged on the back of a flush barn, a freestall barn, in a couple different ways. It can be parallel to water flow and you just funnel the flow in. However, more than likely, just the way things work out and for cost of construction, it's normally done perpendicular to the flow. And so this is just one example on the right where the water would flow down, hit a curb. Perhaps a sand lane is integrated into that flow as it flows from right to left, and then it does a hairpin turn and then flows into that basin. The layout's really going to be dependent upon what's there on site already and what makes this most cost effective. Here's a picture of it in operation. You can see the mat formed. This is a very choppy mat. This is one with high hydraulic loading we'll talk about in a bit. The water from the freestall flows out of the barn, makes a left turn 90 degrees, and then flows into the basin. The flush water from the parlor, Milliken parlor, and holding pen come down the side of the barn, and it enters the basin near the ramp, basically under the red rail on the left picture. Any water that's to go through this really needs to enter ideally through the ramp or across the ramp or as near to that point as possible to prevent turbulence, which would have a negative effect on mat formation. This is a view of a second installation we'll talk about, a much less hydraulic load. You can see there's not quite the undulations and cracks in the mat above. Pull plug up on the left in the picture on the left, and then the picture on the right is a view of that pull plug during cleaning. There's a great deal of distance between the PPSB at this installation and the receiving lagoon, so the operators opt not to pull the plug for fear of having that line clog. And they don't seem to have a problem with that in terms of unloading the solids. These pictures here are of that pull plug in operation. The one on the left is between flushes, so you always get a little bit of a trickle of water. You can see the line on the baffle where the hydraulic jump occurs during the flush, and the right is a picture of that same pull plug during flush. So we took a look at two dairies, a little bit different, kind of similar in size. The BR dairy and FM dairy, the names have been changed to protect the guilty here. BR is a sand-bedded dairy. Their setup is one where they've got 4 flush lanes, 2 on the right side of the barn, 2 on the left. They flush 7,000 gallons down the right side, so 3,500 gallons per lane. They have 1 tower. It takes them about an hour to recharge that tower before they can then flush the left side of their barn. That means that the PPSB is seeing about 7,000 gallons each flush, because by the time that hour passes, the water is evacuated, the PPSB by and large, and they do their flush 2 times a day, morning and night. FDM dairy is mattress bedding with cedar shavings. Similar herd size. Also, the barn is similar in design. They have 4 lanes, but they have 4 valves, and they've got 2 towers. So they just walk down the line, and they'll hit valve after valve after valve in sequence. So they end up sending about 28,000 gallons over the course of maybe 10 minutes, perhaps less. So that hydraulic load is much greater. As you saw in the pictures before, the first pictures with the undulating, very rough-looking mat. That's the one with the hydraulic loading that's higher. They flush 3 times a day. So higher concentration of solids in the morning and presumably approximately half the load in the afternoon and the evening. So our first step in looking at this is hydraulic loading. We've been working on this now for about 6 months, so kind of in the infancy, particularly with COVID, not being able to do a lot of travel, that sort of thing. But BR dairy, that 7,000 gallons applied to the operational liquid level, so the surface area at about 4.5 to 5 feet in depth. This is calculated, I think, on 4.5 feet. That ends up being 4.7 gallons per square foot. The linear hydraulic loading, 350 gallons, that's across the maintenance ramp, so 20 feet wide. And then the weir loading rate is on that 6-inch pipe. 3.5 cleanouts per year. So they are cleaning out every 3 to 4 months. We just split the difference there and calculate the number of cleanouts per year. F to M dairy, much higher load. That's, excuse me, I misspoke before. Both of these are, I think, are on a 5-foot operational water level. The F to M dairy, the dimensions are not much different than BR. The BR dairy is the 20 by 20 flat floor that we saw before. FM dairy is maybe 3 feet wider, 4 feet longer, but very, very close in size. So the hydraulic loading is much higher because they're flushing essentially 4 times the amount of water through it. And with the cedar shavings, they're running 10 cleanouts per year every 5 weeks. Probably not terribly ideal, but that's what it is. So we tested these different things for these different areas in the match for nitrogen, phosphorus, and potassium. The actual weight of the phosphorus in the P2O5 is about 44% of what we see here, and that's reflected in the numbers there. So that's the actual weight of the phosphorus. What we see at the sand dairy, the BR dairy, is stratification. You get 2 feet on top and 4 feet on the bottom. The 2 feet on top is undigested fiber. The 4 feet on bottom is undigested grain and a lot of kind of sandy loomy. Their sand lane's about 60–70% effective. So we sampled from both, and note this is 6 feet all the way up to the curb. Their lower hydraulic load means that they can allow this thing to begin to breach the top of that curb before they have to clean it out. F to M dairy is a little bit different. The high hydraulic load means they have to clean it out when those bottom top interfaces meet. And it is still about 1 foot to 1.5 feet below that curb height because of the hydraulic jump associated with that hydraulic load. Now, it is all fiber throughout that PPSB for FM, but we did notice a difference between what appeared to be older fiber and newer fiber. Older fiber maybe closer to the top or closer to the back by the pull plug. Newer fiber, maybe lower, but definitely more towards the maintenance ramp. And we did see a significant difference in nutrients in those. Interesting thing is the nitrogen concentration between the two dairies in the old fiber for FM and the top layer at BR, scary close. No, we needed to consider nutrient production to figure out how many nutrients were being retained. So we referenced Wasabi for production, and then to account for the cedar chips, we talked to the supplier of the cedar chips, got the volume being supplied per annum as well as the weight, and then referenced some Canadian research for the nutrient concentration in stem wood of conifers. So using that, we're able to produce or generate the annual production for the BR dairy and got percent retention as reported here per annum. FM dairy, the contribution from the wood chips negligible. But this was a significant difference in terms of retention, and we ask ourselves why. We turned to literature and see what they had to say, and there's not a lot in terms of liquid solid separation, sort of pre-treatment screening for nutrient retention. There was one paper talked about mechanical screens, 1.5 millimeter pore size. Very little nutrient retention can be expected based on the size of particle being retained. And we looked at a 2-stage weeping wall. They reported a little bit higher nutrient retention, and it makes sense. Although the mechanical screen is producing a very consistent quality of water and very consistent quality of solids, the weeping wall, presumably the PPSB, start out with capturing coarser solids. And then over time, as they begin to fill up, the nominal pore size, equivalent nominal pore size decreases, and you are capturing a smaller and smaller particle. And so it makes sense why they would have greater nitrogen and phosphorus retention. TKN being ammonia plus organic nitrogen, does not include nitrate, nitrite, but that's probably negligible anyway. We compare that to the PPSB and the sand bed PPSB, not the same, but it's in the ballpark. But again, that cedar chip PPSB much, much higher. And again, why? So our best guess at that why is that the cedar chips, particularly fresh, not recycled cedar chips, are providing absorption and adsorption to this. Adsorption being that organic particles are sticking to larger organic particles, similar to activated carbon, although not as effective using the cedar chips, but it's still occurring. The absorption coming from a bit of a discussion with the cedar chip provider, them saying that these are extraordinarily dry chips, and we need to investigate the moisture content. But they would tend to, being dry, absorb more fluid than or moisture than something that had a higher moisture content going in, and perhaps smaller particles, dissolved particles, are being absorbed into that wood matrix along with the moisture. So that's something to look at as well, and will become part of our next steps. So what we need to do is definitely look at create a composite of the nutrient concentrations within that PPSB at FM Dairy. We assumed a 50-50 split on the new versus the old fiber. It's probably not right. That was just a visual observation. So sample more locations, figure out what that is. Evaluate the effects of solids and hydraulic loading. What happens if we spread that flush out so it's not seeing that 28,000 gallons? What's the effect? Better or worse? And solids loading as well. What happens if we only flush twice a day versus thrice a day? Does that have a positive or negative effect? Develop the system mass balance by trying to get a better handle of what the cows are actually producing versus using Asabi as a reference. Also looking at the lagoon, finding out what's going on there and presenting a whole system mass balance. Explore that adsorption and absorption a little bit more thoroughly. And look at the temporal changes because of that nutrient concentration difference between the old and the new fiber. Why is that occurring and why is there a difference? I believe there's a Q&A on the back of this live, but if you need to get in touch with me, email is the best way to do so. And I look forward to taking questions and hopefully hearing from you in the future.
Okay, we'll take questions for Tim now. I see Tim's on and unmuted, so do we have questions? So you had mentioned, Tim, that this project was underway during this COVID period of time. Is this ongoing project? You continue to be or plan on continuing to collect additional data, and what kinds of information would you collect if you're continuing?
That's correct. As mentioned in the presentation, this has been done kind of by this is what works, and it's been done for a specific range of dairy sizes. And it's just sort of been a cookie cutter approach. They don't have good design criteria in terms of system optimization. And that's why we began looking at hydraulic load from a couple different perspectives to begin to put that together to develop sort of a guide on how one might go about designing this maybe for a 300 head or a 400 head or 500 head dairy versus 150, give or take.
Sure. And then any comments you might, these are questions that I had, just to go ahead and post a few from me before anybody puts in the chat box, but experiences in doing these kinds of applied projects on farm, what tips and pointers might you have for others in the audience that make those kinds of relationships successful?
Well, I'm just getting going on this. I came from the municipal wastewater side. But I think that the experiences, I think the challenges are very similar, where it's a very practical approach, what works, very budget mindful. I think that getting out in the field, making those relationships and finding out what works for different people is really important, and not making a lot of assumptions going in. I think one of the most difficult things from a scientific or academic sense when you're doing this is the tremendous amount of variability involved on farm. Just sampling, for example, on a flush dairy, trying to capture a representative sample of that flush is, I think, nearly impossible, because you're going to have constituent differences in that flush water, whether it's spatially left to right across the stall as it's being flushed, as well as temporally. So you get what you get at the first part of the flush is probably very different than the last part. And so how do you combine that, composite that to get something that's really representative is very challenging.
Okay. And there was a question came in from Rick Stoll, and I think that you kind of addressed that, but he was asking if there's any comment on sampling ease or challenge of sampling, and it sounds like you kind of addressed that in your prior comments there.
Yeah, I think so. And hearing the presentation again, 90% solids retention, that's rather subjective. I think they're talking just, very, very coarse solids, because what's really the difference between a dissolved and non-dissolved solids? It comes down to a standard method, I think. So for whatever it's worth.
And one question here from Washington. Is the PPSB system typically a pre-treatment to a mechanical separator, or does it sufficiently remove solids from a lagoon maintenance standpoint?
It would be the latter of that. The guys and the gals that are doing it to try to reduce the amount of lagoon dredging they have to do. And so these are flush systems. By and large, these are people who were looking at weeping walls, but they're very concerned over some of the maintenance that they saw with the weeping wall, with the binding and the plugging of the slats, and how to get around that. And we're led to believe, although we haven't interviewed everyone that owns it, just a few, that they're very happy with that, with the maintenance on that, and that the system has met their expectations. Very little solids accumulation in the lagoon after the installation of this.
Okay, well, thanks for answering questions, and thanks for making a presentation today. Before we go ahead and move on to try to keep ourselves on time here. So our next presentation is going to be on the topic of decision support systems for dairy and swine manure. And so we'll start that up now.
Hello everyone, my name is Sudarshan Verma. I'm a postdoctoral researcher at the University of Arkansas, and my talk is about developing decision support tool for dairy and swine manure management system. Coming to our project overview, there's a huge demand and multiple pressures on the agriculture sectors due to continued global population growth, increased extreme weather change, and the resulting variability in reliable water resources. That requires water recycling to become an integrated part of agricultural water management. Simultaneously, the dairy and swine industry has grown steadily in the past decade, and it is expected to increase. Hence, there is a need for and a drive towards innovative technologies that can better utilize and recycle water resources for food production. So the goal of this project is to develop a robust membrane-based electrochemical engineering technology to enable manure treatment and water nutrient recycling for food production, and also to develop a decision support tool that facilitates the selection of liquid manure treatment technology based upon local agriculture needs and nutrient balance requirements, with a focus on life cycle assessment model that projects the environmental and economic impacts for manure treatment technologies through multi-criteria decision making. There is a substantial heterogeneity in dairy and swine manure management practices across different farms, size, and geographic locations. These multiple individual practices include different collection methods, water usage for cleaning, bedding selection, handling, processing, and application, etc., which highly impacts the final effluent and solid nutrient characteristics. So in our decision support tool, we will recommend manure management alternative through the decisions made based on 3 primary criteria, that is economics, environmental impact, and the technology performance. Further, each of the criteria will have sub-criteria that are calculated or ranked with respect to many treatment alternatives that the user is allowed to select. For example, the different treatment technologies include lagoon-based systems, anaerobic digestion, solid liquid separation, membrane technologies, composting, etc. Further, the sub-criteria for economics will include capital cost, operating cost, cost savings, and revenue generation for each of the treatment methods selected. Similarly, environmental impact will include global warming potential, acidification, eutrophication, and ecotoxicity. Finally, the technology performance will be ranked based on the survey question or scoring methods, which will be discussed in later slides. The decision support tool has 4 major components. First is the user input sheet, where all the waste generation and treatment processes will be occurring. Next is the cost benefit analysis and life cycle assessment. then analytical hierarchy process for decision making, and the Python programming to read and perform calculations. The current prototype manure management tool is an Excel-based platform with empirical performance-based mass balances for several manure management alternatives, representing current and emerging technologies and practices. The tool contains different subcomponents related to the collection and treatment methods, and also the user will be provided with placeholders with a reference guide to choose the recommended values, or they can input their own farm values. These components include different cleaning methods such as flushing or scrap systems, and the amount of water used for cleaning, and different bedding methods, organic bedding including sawdust, compost, or inorganic bedding such as sand, and amount of bedding used per animal. And the different technologies include storage pond, lagoons, anaerobic, etc. And also we have IPCC greenhouse gas emissions, and finally the decision-making process. To give an example, we have the process flow diagrams, which include different collection and treatment methods. And we have performed the pre-calculated mass and energy balance for each of these scenarios based on the number of animals and the manure generated. This is one of the scenario where the user has flushing system with sand bedding, followed by sand separation lane and treatment through anaerobic lagoon system. We also included recycled flush water to clean the freestyle barn and the recycled sand bedding to the cows, where all the components are included in our calculations. So these are a few more examples for a simple storage pond with flush system, and other is the anaerobic digestion scenario, which treats the scrap manure with organic bedding, followed by solid liquid separator. Going forward, okay, this is the user input sheet in which the purple cells have the recommended optimum values of minimum to maximum range, while the first three options are used for animal type and the weight selection by the user, and the adjacent red colored column cells are used for the user input. Similarly, we have the same option for different variables like bedding, flushing volume, manure characteristics from milk barn center, etc. Once a user creates an input file like this, they can run the program and tell it to read their file. Then the program reads those inputs and checks validity and starts performing calculations based on the scenarios that we have defined. This would also include cost analysis and LCA. Then finally, the results are output to an Excel file. This tool also provides a reference guide with the recommended values for different components of the manure management system, where the user can look up for values. And the treatment and mass balance calculations would include the following. For example, the total waste generated from the farm. We have the manure characteristics of all the manure generated, like total solids, volatile solids, nitrogen, phosphorus, and potassium. And the treatment calculations are performed considering the loading rate, treatment volume, treatment or separation efficiency representing different treatment methods. And we have the final effluent and solid properties. Also, it includes IPCC Tier 2 greenhouse gas emission equations for all the treatment scenarios to understand the environmental impact. This is an example for a lagoon system calculated for 180 days, which include daily organic loading, sludge accumulation volume, storage volume for a 25-year, 24-hour storm event and freeboard, and the gas emissions. Similarly, below we can see the scenario for anaerobic digestion. We have all the engineering design factors. And once we have the output from the earlier slide, that is the treatment technology file, we use those values to calculate the environmental impact using the reference values from the LCA software CIMA Pro. And finally, we use all the values from the technology file, environmental impact and economic values to consider the decision making. Please listen to the presentation from one of our team member, Erin Scott, where we have the cost and benefit calculations linked with this decision tool. For scoring the treatment technology performance, we'll be following the scoring method offered by Nutrient or by some survey questions in future. And finally, once we have all the output values, we use analytical hierarchy process to assign priorities on each alternative by identifying the goals or the importance of attributes hierarchically. This hierarchy structure is composed from low to high levels on the basis of criteria and sub-criteria, and gradually leads to the decision of best manure management alternative. Coming to the conclusions, for now we have developed 20 different dairy manure management scenarios with all the mass and energy balance. This mass and energy balance values are nicely linking with the economic evaluation and LCA. Also, we have prototyped the analytical hierarchy process for testing the decision algorithm to select and rank alternative solutions under local constraints. Also, Python programming is being developed and we are test running the code. Next, we are in the process of developing the model for swine manure management. Finally, I would like to thank the audience for listening and the conference organizers, our team members, and funding USD NIFA. And here is my contact details. If you have any questions, I'll be happy to discuss. Thank you very much.
Okay, we'll take questions now. And then after questions, we're going to have a bio break from 10:50 to 11:10. So questions for our last speaker. So maybe I'll go ahead and ask Sampali. So how are you going to be doing additional trainings? How are you going to try to get this out and do your public relations campaign for users and so forth?
Yes, yeah. So we are planning this tool will be available on a online web user interface, and also we have extension team we are planning for webinars or like some workshops to hear the producers' thought on that, how they wanted to see the software or like model wanted to develop the decision making process.
So do you see this tool being online, or is it something that would be kind of a standalone application where you download on your computer, or how do you?
No, it's not like a software package. That's what we're discussing. For now, we thought of it could be like an online tool on the website. So where the user can input all the values and they can get the additions with the different alternatives.
Okay. And one question that did come in is, what information is most limiting for development of the tool?
Yeah, the main thing is data sets. Like we have different technologies of different treatment methods, even with the, for example, like solid liquid separators or different treatment methods. So main thing is data sets, how we wanted to design the treatment efficiencies, like given a number of animals per farm, like the total volume being generated. So the main thing is the data set, what is the efficiency provided by each of the treatment methods. So that's what we are lacking. That's why we just came up with the user input or with the recommended values. So that's what we are working on now.
And one question came in, are there any dairies that are actually utilizing the tool?
No, not yet. So we are just in the developing process. It started a year from now project. So we are in the developing process now.
Development.
So, yeah.
And then another question came in about, could you add some more information on the cost saving sub-criteria in your economics model?
Oh, yeah, that's what I mentioned. We have a team member from our university, led by Dr. Jenny Pop. And we have a presentation coming up in the next one after the break. Yeah, so I'm not a real expert on the economics, they are dealing with the economics. Yeah.
Okay, so the next talk after the break, we'll get into that cost benefit a bit more in detail by, I think it's Scott Aaron.
Yeah, exactly, yeah.
Okay. Any other questions that might come in from the audience? Okay, not seeing any, but we'll have part 2 of this after the break. So schedule at this point, I'll put it up here again on the screen, but we'll be taking a bio break from now until 10 minutes after 11 Pacific Coast time. So we'll see everyone back at that point. So thanks for joining us this morning.
And land application activities may be problematic. And additional manure processing might be needed, but farmers also need good information and tools to make best business decisions in managing these valuable nutrients on farm. There are a lot of opportunities for cost savings, revenue generating co-products, and environmental stewardship, but there can also be high costs associated with these manure management opportunities. The purpose of this study is to develop cost-benefit analyses for multiple manure management technologies and processes. And like I said, this analysis will integrate into a decision support tool along with environmental impact and technology criteria. And this chart shows some of the sub-criteria that we consider for each of the main criteria. And so the economics will look at capital costs, operational costs, cost savings, and revenue potential. So for this project, we are considering all things manure. So looking and evaluating everything from collection to treatment and storage to land application. And like I said before, for this talk, I'll focus on modeling capital costs for different solid liquid separation technologies. Solid separation removes coarse solids from the liquid stream, and this can be valuable because it reduces manure volume going into storage, and so it can reduce the sludge buildup in the lagoon, as well as reduce odors. And it can also reduce bedding costs and the cost of transportation and application to the land because there's less water in the solids, and also liquids can be pumped rather than hauled to the field. But separation also comes with added investment and operational costs, as well as the management of now 2 different waste streams. And so the economic analysis will help understand the trade-offs between these costs and benefits. So in order to do this, we need to first define what those costs and benefits are. Focusing on costs of solid liquid separators, we want to be sure that we account for all of the major cost components. And a big challenge I have, well, my background is on surface water quality and not on agriculture or economics. So I'm still, getting a feel for this terrain and how data collection goes and sort of what the important economic factors are. And so from the literature and reports and the data that I have collected so far, it looks like the major cost components for solid liquid separation includes the separator itself, the installation of the separator, other equipment that is not in the list price for the separator. So things like washers or sprayers, electrical, and installation for these things. Adjacent infrastructure, which would include concrete slabs and building and other earthwork, plus that installation, and then transport of manure into and out of the separator system. And I will say I am happy to receive input from others who have alternative suggestions to these components or to this overall approach. So after we've defined what those major cost components are that are important to the economics, we need to assign values. So I'm currently collecting data for each cost component and plan to model these for each separator type that we're evaluating and across a range of farm scales. So under perfect conditions, I would have reliable and comprehensive cost information for all the important cost components for all types of separators and under the proper range of farm sizes without gaps in data across scale. So I quickly found that data collection is challenging, and I cannot expect this level of data, especially when considering I'm doing this similar analysis across several other manure management technologies. So a question I'm trying to answer is, where should I direct my focus for data collection? We have opportunities to work with industry partners who may provide cost estimates, but their time is extremely valuable and our request needs to be focused. So just generally, I'd like to know, how do costs change with scale? So maybe we can focus our efforts. And so are there breakpoints where costs increase more significantly at certain farm sizes? And if so, what are those breakpoints? For example, do these make sense? 100 cows, 200, 500, 700, 1,200, 1,500, 2,500, and 5,000. Are there significant breakpoints at these farm sizes? And another challenge is we are looking at swine operations as well. So we'll be having to evaluate sort of different animal types and numbers of animals. And then one other question I have is, do these, if there are breakpoints, do they really matter based on the variability in cost due to other driving factors? So even if we know that costs will increase for a separator from, say, 400 to 500 animals, will that cost be visible when considering differences in other factors? So if we look at this little graph on the lower right, yeah, if I know that I just need one separator up until 400 cows, and then after that I need two separators, so the cost per cow, you're going to see that sort of quick increase. But just in my data collection efforts, am I going to be able to capture that type of shift if there's, depending on the level of variability there is inherently in costs across farms? So I do have some preliminary data to present for a two-stage separator, which is a slope screen followed by a roller press. These four graphs represent the same data set for modeling capital costs of a two-stage separator. And this would be total capital costs, but I would have similar sorts of data for each of those cost components. The two top figures show total capital costs. The two bottom figures show capital cost per cow. The left panel show the number of animals as the explanatory variable, and the panels on the right use volume of manure processed. And so the point of this slide is not necessarily to look so closely at the costs, because there are some qualifiers to these data that I need to address before I actually finalize this evaluation. But rather, really the point here is to express a question, and that is, what's the best explanatory variable to use to model this information. I've seen it done with number of total animals, number of milking animals, and manure volume processed. And so, you know, having data reported in these different ways makes it kind of hard to use literature data to build models. But then also just generally, what is the most realistic and meaningful way to model capital costs? So ultimately, the goal of all of this is to calculate costs for each of those major cost components within a technology or process and present this economic output to the person using the tool. So really, the output will address the relative differences between different options for alternative manure management, and is certainly not intended to provide actual cost estimates for any given farm. But we still want this, you know, these economic outputs to be valuable in some way. And a final question I have right now is, what economic information is most relevant to farmers? Are they interested in comparing options based on a total recovery value, or, you know, which is like an annual cost of ownership? Or are they interested in something like net present value that evaluates cash flows over a given period of time, like 5 or 10 years? Again, these results, whatever they are, will integrate into the decision support tool and will be presented to the user. So right now, it seems like I have a lot more questions than answers. And so next steps are to find answers for these questions and also obtain reliable cost data to really start modeling the solid separation equipment. And then after that, I'll move on to other manure management technologies like anaerobic digestion, fine solids recovery, and water recovery. So I'd like to thank the USDA National Institute of Food and Agriculture for funding this research. Also a big thanks to my research partners on this grant for their guidance and support. And then finally, thanks to you for your time. I'll try to answer any questions you might have, but I also want to say I'm very interested in any comments and suggestions right now or in the future. So please feel free to contact me by email or phone, which is shown up on the screen. Thank you.
Okay, thanks, Erin. And fortunately, I was able to finally get the right presentation up there. I was looking at yours, but I obviously clicked on the previous one when I booted it up, so sorry about that. Questions that are come in for Erin, please put in the chat box. And while we're waiting for any of those to come in, given your project team and their awareness of other researchers in the manure management field, I'm assuming you guys are aware of the IFSM model that was developed by Al Rotz. Al's currently at State College at Penn State and with ARS. And I know that Al has quite a lot of information with regard to system costs that are embedded in his model. I did a sabbatic with him, and I know that through the years he's been pretty generous about sharing information. So I would recommend you reach out to Al, and that may help you in your development process there.
Okay, yeah, that's great. Actually, I've not heard of that group or that project. Can you say Al's last name again?
Yeah, it's ROTZ, Al Rotz.
Okay.
And members on your team there, Nebraska and Missouri should know Al. So, yep. Any other questions for Erin at this point? I got a quiet bunch here after the break. So, okay, well, it's nice to see progress on this project. And how long will your project be running? What's the year span?
It's due to COVID, maybe a little bit extended, but I think we've got about 4 more years on the project. But of course, we hope to have a good comprehensive prototype, not, much sooner than that.
Sure. Okay. Well, great. Okay, we'll look forward to additional updates on it. Challenging project, but certainly going to be worthwhile, because I think the goal is to have something that's fairly user-friendly at the producer level. Is that correct?
That's right. Yes.
Okay. All right. Well, I'm not seeing any questions come in, so we'll thank you, and thanks for being on with us today and answering questions.
Thank you.
Okay, so our next talk is due to start at 11:30, so we're just a couple minutes shy of that, so I think I might drag my feet here for another minute or so before we start that up. So we have 4 more presentations yet on this technology session. Appreciate everybody hanging in there for this marathon. This was one of the longer sessions that of the 7 that we have scheduled for this week. Okay, I think we'll go ahead and move on to this next talk. Rick Stoll mentioned that if anyone has installation cost info that can be shared, Aaron and our team would be interested. So yeah, please do get in contact with them. Chasing down these details can be pretty challenging and time consuming. So, okay, so our next talk takes into consideration the use of centrifuges for removing solids on farms. So by Li Chen.
Hello, I'm Li Chen,
Waste Management Engineer. I'm going to be presenting evaluations of on-farm centrifuge and screen on removing solids and nutrients from flush liquid dairy manure with 2 co-authors, Kevin Kruger and Howard Niblin. Kevin is here with me. He will also be presenting. All of us from the Department of Soil and Water Systems at the University of Idaho. For today's talk, we'll give you brief project background information, what we did, what we have found. So first, project background information. Idaho has a strong dairy industry and ranks among the top 5 milk producing states in the nation. As a byproduct of milk production, large amounts of manure are generated each year. Some ag dairies use liquid manure handling systems, either flushing their manure lands or mixing their equipment clean water with vacuum slurry manure from their manure land. That results in large amounts of liquid dairy manure. Solids and nutrients presented in liquid dairy manure pose challenges to manure handling processes. Most ag dairymen are familiar with the benefits of solid liquid separation and have installed primer screens that separate coarse particles from their liquid streams. A few dairies have incorporated secondary solid separation technologies, such as centrifuge and secondary screens, into their manure handling systems to realize higher solids and nutrient removing rates. dairy producers have realized that separating solids and nutrients from liquid dairy manure is a critical step to realize better manure management. Attica dairymen want to learn more about solids and nutrient separation efficiencies by centrifuge and screens to make informed decisions on upgrading their solid liquid separation technologies. The objective of this study was to evaluate centrifuges and screens performance on removing solids and nutrients from liquid dairy manure and on affecting ammonia emission from their treated liquid dairy manure. What we did, we conducted year-long evaluations of on-farm centrifuge and screens on removing solids and nutrients and on affecting ammonia emission from flush dairy manure. Flush liquid dairy manure samples were collected monthly before and after screens and centrifuges from commercial dairy in southern Idaho. Meanwhile, screen and centrifuge separated solids were collected from the same dairy. The collected separate solids were analyzed for nitrogen, phosphorus, and potassium by a certified commercial laboratory. The collected liquid samples were analyzed for total suspended solids in our waste management laboratory at the University of Idaho Twin Falls Research and Extension Center. Ammonia emission from the monthly collected liquid dairy manure were also evaluated using ammonia passive samplers outside the waste management lab under seasonal conditions of the year. Ammonia emission rate was calculated based on the durations and ammonium nitrogen concentration from the agua ammonia passive sampler tests. Here is a liquid manure flow chart on the dairy. They have received pit where the barn milk powder clean water was mixed with a vacuum truck collects slurry manure. From there, pumped to a sand lens where some sand removed, then flowed to a pit, and went through two primary screen in parallel, and then to the two centrifuge again in parallel, and went through to their lagoons. From there, applied to the cropland and their irrigation systems. We collect liquid manure from the location. We mark here 135. That's before screen, after screen, and after centrifuge. Also solid from screens and centrifuge that's marked at 2 and 4. So Kevin will be talking about the ammonia test. So go ahead, Kevin, please.
Yep, thank you, Lita. The passive ammonia samplers were used to determine the time average concentrations of ammonia in the headspace of 5-gallon buckets containing the monthly collected liquid dairy manure. 4 replicates per treatment were tested by the passive samplers every month during the 1-year test period. The disassembled components of the passive samplers were thoroughly cleaned before placing them into the headspace of the buckets by rinsing with deionized water and soaking in 1 molar hydrochloric acid, rinsing again with deionized water, and then drying them in a clean hood. The passive sampler filters that you can see, that's number 3 in the figure, were prepared by saturating a clean filter with 100 microliters of 2% citric acid and air drying before assembling the samplers. Next slide. At ARS, researchers helped us to analyze these samples. 5 milliliters of 1 molar potassium chloride was pipetted into the centrifuge tubes with the filters. The solution was tested for ammonium concentrations using the QuickChem system. Next slide.
So we'll move on to what we found. So the picture shows a centrifuge and a screen separate solids. Left one centrifuge separated. We can see the screens only get the longer fiber out of the liquid stream, but centrifuge had a capacity to remove much finer particles. This is total nitrogen in the separate solids. The blue one is from screen separate solids. So this figure shows the total nitrogen concentration in the centrifuge separate solids higher than that in the screen separate solids. A year-long average of 9.2 pounds per ton of total nitrogen in the centrifuge separate solid compared with 5.4 pounds per ton in the screen separate solid. Here's the phosphorus in the separate solids. It's much higher concentration in the centrifuge separate solids compared with that in screen separate solids. A year-long average of 8 pounds per ton of phosphorus versus 2 pounds per ton in the screen separate solids. So they're almost 4 times higher in the centrifuge separate solids. Here's potassium concentration in the separate solids. Again, a centrifuge separate solids have higher potassium concentration, a year-long average of 7.2 pounds per ton of potassium compared with 4.4 pounds per ton in the screen separate solid.
Here we see total solids on the y-axis and time on the x-axis. The treatments before the screen, after the screen, and after the centrifuge were found to be significantly different for total solids. However, time was not found to be significantly different. Next slide. This has the suspended solids on the y-axis and time on the x-axis. The treatments before the screen, after the screen, and after the centrifuge were also found to be significantly different for suspended solids. However, time was not found to be significantly different. Next slide. Here we have ammonia emissions rate on the y-axis, excuse me, and time on the x-axis. The treatments before the screen, after the screen, and after the centrifuge were found to be not significantly different for ammonia emission rate. However, time was found to be significantly different. Next slide. So here we have the ammonia emission rate as correlated to suspended solids. For each of the treatments, there was a negative slope relationship indicating that suspended solids decrease the ammonia emission as the ammonia emission rate increases. Next slide. Here we see the ammonia emission rate as correlated to temperature. For each of the treatments here, there was a positive slope relationship indicating that as temperature increases, the ammonia emission rate also increases. Next slide.
Okay, move on the take-home messages. From this test result, we can see centrifuge can further remove finer particles that cannot be removed by primary screens. Centrifuge separate solids contains higher nitrogen, phosphorus, and potassium, especially phosphorus. Again, average of 8 pounds per ton in the centrifuge separate solids compared with 2 pounds per ton of the phosphorus in the screen separate solids. Ammonia emission from raw liquid manure screen and centrifuge separate liquid manure did not show significant difference. The most influence factors for ammonia emissions from a liquid manure were ambient temperatures and suspended solids content within the liquid dairy manure. So this study was supported by USDA NIFA via a Western Sarah project. Also, many thanks to the scientists at USDA ARS Kimberly Research Station. So any questions or suggestions, please contact me at lchin@uidaho.edu or call me at 208-736-3615. Well, thank you very much for your time and attention.
Okay, nice to see some good solid data on how the performance of these systems work. I know that's something that's been a challenge for a number of years. So do we have questions for speakers? Leedy and this technician? Anybody want to submit something there? I'm glad you were able to characterize the changes over the seasons and do that on a monthly basis. I guess looking back at it, is there anything you would do differently or additional aspects you would look at if you had to do it again?
So I would want to try to characterize the correlation between the suspended solids and the ammonia emissions rate. I would probably do some kind of, I would attempt to do some kind of controlled analysis where I varied the suspended solids content a little bit more. We ran into problems with basically not enough maybe variation in the suspended solids content, so it didn't give us that much of a slope. So, you know, if I wanted to do, I feel like we need sort of a validation part where we try to, you know, figure out if, you know, varying the suspended solids a little bit more, maybe with dilutions or something, would affect the ammonia emission rate more or less. So that's what, I mean, that's where I would go with that.
You know, another thing I want to mention, since this on-farm study, we really cannot control the farmer's operation. So some, that's kind of since, I don't know how we'll do a better sampling in that regard. Since we did another test on another farmer, they also use a centrifuge. Look, sometimes the result, especially from a commercial nurse, is kind of a little frustrated for us. Since you look at their liquid flow rate, since they add some they call bottom remove pit, they did a V shape. So when we collect liquid manure, even we try at the same time, but to me, it was still not the kind of same manure before to screen, after screen, before centrifuge, after the centrifuge. So this kind of things is still not good, like we did something research in our labs.
Yeah. And on the other hand, I think it's really beneficial to be having these really applied analyses done so that we know what's going on in the field. And so there's a question that did come into the chat. Were mass recoveries considered as well as nutrient percent and recovered solids? So we're actually able to do some flow measurements and kind of do mass flows.
You know, that's kind of a challenge. We didn't do that because again, when we do the sampling, since they add so many different paints, it's really hard to get a same liquid. before and after. So that's why we try to do that, I guess. We look at the data, especially from the commercial lab. Sometimes it doesn't make any sense. For example, we even get a higher solids after the centrifuge, or even after screen sometime. So that's why we didn't do the mass balance calculation and other things for the reuse flushing. There even we don't add any meter to measure all this rate. When we talk with the dairymen, they said no, we don't have kind of the numbers or figures how many percent we reuse. Their flow really not straight from screen centrifuge to the flushing page reuse. So there are some at some point that will direct connect from the flushing page to back to the lagoon or to the centrifuge. That's kind of a challenge. We didn't do the mass balance calculate at this time. Maybe we'll try in the future time.
Yeah, it sounds like the plumbing was kind of challenging, and we had a similar project. We were trying to do this mass flows, and yeah, tight systems are rarely exist on the dairies. You always have some side streams coming in and going out, so it gets to be a real challenge. Okay, well, thanks for that presentation. Good to see some data, performance data on these centrifuges. I know they're definitely gaining acceptance out here in the Northwest, and so now we have some good solid data to base some of those decisions. So.
Well, thank you, Joe, and our audience. Another thing, if you're really interested to hear what the dairyman said, we have a video session tomorrow. You can hear much more information regarding the centrifuge from the dairyman point of view. Well, thank you very much.
Yeah, we've got some video case studies, as what Leedy's referring to, tomorrow afternoon. And so if you want to actually hear what the producers have to say about these systems and see some pictures and video of those systems running, please join us in the afternoon tomorrow. Okay, we'll go ahead and move on to the next presentation. And that's going to be a presentation by Vishnu Pandey. So go ahead and boot that up now.
Distinguished session chair, my fellow speakers, and all participants. My name is Vishnu Pandey, and I am a grad student in Water Resources program at the University of Idaho. I'm also working as a research assistant at University of Idaho Twin Falls Research and Extension Center. The goal of my talk today is to introduce some of the nitrogen recovery technologies that are currently being studied for their use in recovering nitrogen from animal manure. The livestock industry over the last few decades has seen a major transformation. It has shifted from traditional to a more intensive form of animal rearing. Today, we see a lot of confined animal feeding operations that have a large number of animals in a confined space. As the global demands of meat and meat products continue to increase, the livestock industry is expected to grow even bigger. These intensive livestock farms produce a huge amount of manure in a confined space. The nitrogen in manure has been linked to causing several environmental problems. The EPA has identified the livestock sector as the major emitter of ammonia in the atmosphere. Similarly, there is a growing concern among environmentalists that nitrogen in manure is contaminating the groundwater. So, it is essential to remove nitrogen from manure. The additional advantage of recovering manure nitrogen is that it can be converted to nitrogenous fertilizers. So there is an opportunity to generate some revenue here. Depending upon the source and manure type, the animal manure contains about 2 to 40 pounds per 1,000 gallons of recoverable ammoniacal nitrogen. This data shows that there is a significant amount of nitrogen present in manure that can be recovered. Presented here are some of the technologies that have been used in industrial wastewater treatment plants to remove and recover nitrogen from wastewater. There are no separate technologies to remove nitrogen from animal manure. and studies are currently being made to test the applicability of these technologies in livestock farms. Although the composition of wastewater and animal manure is different, studies have claimed that these same technologies can be used to recover nitrogen from animal manure as well. So I'd like to briefly talk about each of these technologies. The first one is gas permeable membrane technology. This is a relatively new technology with a simple working mechanism. The figure on the left shows how the system works. Here, a gas permeable membrane is placed either above or below the surface of the manure, and an acid, primarily the sulfuric acid, is circulated inside the membrane. So what happens is that ammonia in the manure enters into the membrane based on differential partial pressure. This ammonia then dissolves in the sulfuric acid inside the membrane to form ammonium sulfate. This ammonium sulfate can then be recovered and sold as a fertilizer. The figure on the right, it shows a tubular gas permeable membrane used during an experimental study. Several studies have been conducted to evaluate the performance of this technology. And as we can see here, the ammonium recovery percentage of this technology is very high. Another advantage of this technology is that it can also be integrated into the anaerobic digesters, which can help to increase the overall biogas yield. Membrane fouling is the major drawback of this technology. The membrane pores might be blocked by manure particles, which can then limit the transfer of ammonia. Therefore, regular cleaning or even replacement of the membrane might be necessary. Next is ammonia stripping technology. Whenever we go near a wastewater treatment plant or an anaerobic digestion facility, we can see this kind of towers. These are ammonia stripping towers that strip ammonia from wastewater. Ammonia stripping can be of different types, but they basically serve the same purpose. The figure on the left shows the working mechanism of a typical air stripping process. In this process, manure wastewater flows downward from the top of a stripping tank, and a current of air is passed from the bottom. This current of air blows away the ammonia present in manure, which can then be captured in acids to produce ammonium fertilizers. Numerous studies have been conducted on the ammonia stripping process, and these studies have reported a satisfactory ammonia removal. But the major issue with this technology is that it is costly and also time consuming. Next is ion exchange and adsorption technology. The first picture here shows a typical ion exchange process. In this process, some porous ion exchanging chemical compounds, also known as adsorbents, are taken inside a tank, and manure wastewater is introduced from the top. Then what happens is that the ammonium ions present in manure exchange with some of the ions in the adsorbents. And when these adsorbents are saturated with ammonium ions, they are taken out and a new batch of adsorbents are refilled in the tank. A variety of chemical compounds can be used as an adsorbent. The picture in the middle is of clinoptilolite. It is a common zeolite that is used in the industrial ion exchange process. Now, there is little literature available on the use of this technology to recover nitrogen from animal manure. And in the little work that has been done so far, the results are not that encouraging. The cheaper cost and easy availability of zeolite rocks are some upsides of this process. But the major issue with this technology is that the ammonia recovery is low. Likewise, other different ions present in manure often interfere with the ion exchange process. The cavities in adsorbents can also be blocked by suspended particles in manure. So this technology has a lot of challenges. Next is struvite precipitation technology. The figure on the left shows a typical struvite precipitation process. Animal manure generally consists of several ions, including magnesium, phosphate, and ammonium. These three ions naturally react with each other to form magnesium, ammonium phosphate in manure. And when the manure becomes supersaturated, the crystals of these magnesium, ammonium phosphates are formed. These crystals are also known as struvites. The figure on the right is the picture of struvite crystals obtained during a lab experiment. These crystals can be used as slow-releasing fertilizers. According to the studies, more than 90% of ammonium ions in the manure can be recovered by this technique. The major positive aspect of this technique is that both nitrogen as well as phosphorus can be recovered from manure at the same time as struvites. And as I mentioned earlier, these struvites can be used as slow-releasing fertilizers. But the problem with this technology is that the manure does not contain enough magnesium ions to produce a large amount of struvite crystals. So in order to get more crystals, magnesium ions need to be added to the manure from outside. The interference of calcium ions present in manure is another major problem with this technology. Similarly, a high concentration of suspended solids in animal manure can slow down the struvite formation process. Next up is reverse osmosis. Reverse osmosis has been extensively used in water purification and wastewater treatment plants. But very few studies have been made on the use of this technology to recover manure nitrogen. The limited studies that have been made so far suggest that this technology can remove a fair amount of manure nitrogen. One positive aspect of this process is that not only ammonia, it removes most of the solid particles from manure. So it also helps in reducing the volume of manure. On the other hand, this process misses the opportunity to capture ammonia and produce fertilizers from it. And because of membrane fouling and blocking by manure particles, pre-treatment of manure is very important for the success of this process. Next one is wet scrubber technology. Now, unlike other technologies, wet scrubber technology has actually been adopted by some livestock farms. These are generally fitted in the ventilations of livestock housing. They trap ammonia coming out of livestock houses and prevent their release into the atmosphere. In this process, the gaseous mixture coming out of livestock farms enters the bottom of the scrubber tower. And as it makes its way up in the tower, scrubbing liquid that can dissolve ammonia is sprayed from the top of the tower. So when ammonia in the gaseous mixture comes in contact with the scrubbing liquid, it dissolves in it and comes out from the bottom of the tower. Wet scrubbers are simple and effective options to reduce ammonia emissions from animal buildings. But lower ammonia recovery is a major drawback of this technology. Another problem is that these scrubbers are often clogged with dust particles. The last method of nitrogen removal I am going to talk about today is the biological method. Biological method of nitrogen removal has been in practice for a very long time. There are several groups of bacteria in nature that can convert ammonia present in manure to free nitrogen gas. Biological method uses the ability of these organisms to remove ammoniacal nitrogen from manure. Several studies have shown that the biological method is an effective method for removing nitrogen from manure. This method usually provides high ammonia removal percentage. But there are also some challenges to the success of this method. The bacterial community is sensitive to the change in several manure parameters like temperature, pH, and oxygen levels. Researchers have argued that this method requires high energy inputs and therefore is costly. This method also misses the opportunity to recover nitrogen and generate some revenue. So to conclude, these are some of the nitrogen removal technologies that are currently being studied for their use in livestock sector. As I mentioned earlier, these technologies have their own positives and negatives. Although these technologies have already been used in industrial wastewater plants, their use in livestock sector is limited. Studies have claimed that these technologies can indeed be used in livestock farms to remove manure nitrogen. But most of these studies were conducted in small-scale reactors, and whether the technologies can simulate the results in full-scale livestock farms is yet to be seen. Because of uncertainty over their success, cost, and sustainability, the livestock farms are found to be hesitant to adopt these technologies. So the efforts to devise an efficient, low-cost, and sustainable technology that can recover manure nitrogen are still ongoing in the scientific community. Before wrapping up my presentation, I would like to acknowledge my major advisor, Dr. Lila Chen, for allowing me to participate in this project. I would also like to thank USDA, NIFA, and Western Share for providing grants for this project. Finally, I would like to thank you all for listening.
Okay, I'm open this up to time for questions and answers. So a pretty thorough overview there of a lot of different technologies. Any questions from the audience at this point? So Bishnu, you obviously, did an overview on a lot of different technologies, but which ones have you had personal experience with, and which ones do you think are the most promising?
That's a tough one to answer, honestly, but it all depends upon how sustainable the technologies are. But based on what I found on the literature, I think the gas permeable membrane and the ammonia stripping technology, they have a high ammonia removal percentage, and I find them promising. But strobite precipitation technology is another important technology because it not only recovers ammonia, but it also recovers phosphorus at the same time from the manure. So it has a dual advantage of both recovering both nitrogen and phosphorus at the same time. But yeah, it all depends upon the cost associated and how sustainable the technologies are.
Okay, thanks. I don't see any other questions coming in, and we had a parallel session this morning, but they ended about a half an hour ago or so. So I think what we'll do is go ahead and move on to our next presentation, and it's by Sarah Wu. So she'll be the next to the last presentation for today. Go ahead and boot this one up.
Hello, everyone. This is Sarah Wu from the Department of Chemical and Biological Engineering at the University of Idaho. In this presentation, I'm going to introduce our study on producing a green nitrogen fertilizer from air and water by a novel electric discharge process. The long-term goal of this project is to reduce our reliance on fossil fuels and associated environmental issues, such as greenhouse gas emissions, by developing a green technology to efficiently manufacture nitrogen fertilizers using only air and water as substrate, operating at room temperature with no need of catalysts. And I'm glad to take this opportunity and share with you our early stage progress. Well, as you know, the abundance of nitrogen gas is existing in the ambient air, but the plants can only live on fixed nitrogen in the form of ammonia or nitrogen oxides including nitrogen and nitrate and nitrite, which are the major components that the nitrogen fertilizers have to offer. Basically, three major nitrogen fixation processes for producing ammonia and nitrogen oxides. Lightning and microbial conversions are two major natural ones, which cannot well controlled for mass production of nitrogen fertilizers because of the inefficient conversion and low producibility. The Haber-Bosch process is one of the greatest scientific achievements in the 20th century, which allowed an industrial scale nitrogen fixation for agricultural production. However, both the Haber-Bosch process to convert nitrogen to ammonia with hydrogen, fossil fuel-based hydrogen gas, and the Ostwald further oxidized ammonia to nitrogen oxides require a substantial industrial infrastructure that consumes massive amounts of energy to provide high temperature, high pressure catalytic conditions, and also creates great volumes of carbon dioxide and other pollutants. Therefore, there has been a growing interest in alternative, greener methods that move away from the centralized fertilizer production. While looking at the very few alternative routes, including biological and electrolysis, electric discharge is the most direct nitrogen fixation route. Both oxidation and reduction routes of the nitrogen fixation can be induced by the plasma discharge of air above or directly in water without catalysts or any external source of fossil fuel-based nitrogen or hydrogen based on these ionization reactions shown here. So nitrogen gas can be ionized to form the nitrogen radicals, while hydrogen radicals can be produced from ionization of water. And a further combination of the radicals from nitrogen oxides without needing to go through the formation of ammonia, while the ammonia can also be synthesized with the available nitrogen and hydrogen radicals. Well, these reactions look very straightforward, right? But much more challenging is to activate these reactions by electric discharge in water and air, as well as engineering of this process for simple operation and better control. By now, the research about liquid phase plasma is mostly for water and wastewater treatment, and its application is very limited due to very low concentrations of reactive species are collected in water. Also, several problems to solved in engineering. For example, pulse power is not easily available. And second, the long-term stable plasma generation in water is very hard to achieve. And third is about the reactor design. All the existing research is using a batch type reactor, and it's almost impossible for the local discharge at the electrodes, because you need electrodes to discharge. It's hard to achieve effective and uniform treatment for the whole batch, as you can imagine. The concentration of fixed nitrogen species is too low to be used as a fertilizer product. So the goal of our research is to find a solution for these challenges by designing and evaluating a novel continuous flow liquid plasma reactor, which is also, you could call it electric discharge reactor. This reactor is not dependent on pulse power and can also use an AC power supply, which is available everywhere, to create stable discharge in both water and organic solutions. And we also designed the reactor into a continuous process. So the treatment is easy and fast. Operation is simple. This work could be a big breakthrough for liquid plasma application, based on which unlimited applicable technologies can also be developed based on the properties of liquid plasma. It can be used for killing bacteria. It can be used for degradation of organic compounds, for environmental remediation, and also for chemical synthesis like the nitrate and nitrogen fixation, and synthesis of polymer plus the natural nanomaterials, as well as the biomedical applications. So the bottom left here is our reactor design. As compared to pin-to-pin and pin-to-plate type of discharge in the typical batch mode reactor, to use a pulse power for frequent exciting of the electrons, which is not stable. In our reactor, the discharge point has moved from the electrodes to a center opening, where the continuity of the discharge current was achieved through the moving of the liquid in the form of a displacement current in the plasma phase. So this structure actually ensures complete treatment for anything that goes through. Experimental setup is on the right. Basically, you need a pump for water flow and a high voltage transformer with one plasma reactor like this. One stable discharge generated in the liquid passing the discharging zone, intensive treatment will be available. So for treatment of liquids, the operation mode can be either continuous passing the liquid through the reactor with a certain flow rate, for which we tested 1 pass and 2 pass. 2 pass just means is passing everything through twice. Or another option is to circulate certain volume of liquid in the system again and again for a certain time, which we call a circulation mode. So in this preliminary study, we use the nitrogen oxide concentration, NOx, which means the sum of nitrite and nitrate in the plasma treated water, to evaluate this discharge process. And our objective include the study of the effect water flow rate and air flow rate for the production of nitrogen oxides, as well as nitrogen oxide production with 1 pass, 2 pass as compared with the circular mode of operation. The results of nitrogen oxides concentration, NOx, in the treated water by 1 and 2 passes with the water flow rate of 50, 100, and 200 mL per minute are shown in this column chart. We can see that for each level of water flow rate, nitrogen oxide concentration for 2 pass is higher than 1 pass, of course, but not twice as much. So the energy efficiency for 2 pass is lower than 1 pass. Lower water flow rate resulted in higher concentration using lower power consumption. So seems like the lower water flow rate is a better choice for improving energy efficiency. Similarly, there is an effect of airflow rate on NOx production is evaluated with the NOx concentration at an airflow rate of 1, 2, and 3 standard liter per minute with the same water flow rate by 1 and 2 pass. It was found that the higher airflow rate resulted in a higher NOx production with lower power consumption. NOx concentration for 2 pass is higher than 1 pass, but not twice as much again. So it seems that using a higher airflow rate is a good way to improve energy efficiency for continuous passing type of operation. But as you can see, the concentration of NOx by 2 pass only reaches up to like 300 milligrams per liter, and seems like more passes won't increase the concentration much more. But what if we need to make a more concentrated fertilizer? A circulation mode of operation by water running again and again in a plasma treating system would be a good choice if only one reactor is used. By operating in a circulation mode for 4 hours and water flow rate at 100 mils per minute, we found that nitrate production keep increasing to a concentration reaching 1,000 milligrams per liter, and show the potential for further increase with longer treatment time or improved operational conditions. At the same time, conductivity increased all the way up to 4,500 Siemens per meter, and pH decreased dramatically in the first hour to around 3 due to the production of hydrogen ions with the NOx ions. We do see that the production of hydrogen peroxide increased up until like 90 minutes before it dropped. High concentration of hydrogen peroxide production indicates highly oxidative species, which means this treated solution could be possibly used as a green disinfectant, pesticide, or fungicide at the same time as a fertilizer. So with these promising preliminary results, the feasibility of efficient and effective nitrogen fixation by our continuous electric discharge process has been proved. To develop it into a viable technology, the next step is that we have to improve the nitrogen oxide concentration by optimizing operational conditions and the parameters, and also achieve a higher energy efficiency, applying a heterogeneous catalyst for higher production rate. Furthermore, to design prototype or work on the scale up of the process for the next level. Finally, we want to acknowledge the support of USDA NIFA for this project. And authors also would like to thank University of Idaho Summer Undergraduate Research Fellowship Program and the College of Engineering Grand Challenge Scholars Program for supporting undergraduate research in this work. We will be very happy to answer any questions you have. Thank you for your attention. Have a wonderful day.
Okay, so pretty intriguing presentation there. Did have one question that came in at this point, and that was, what's the scalability of the technology? Can it be scaled up?
Yeah, well, it is scalable. But since this is a continuous process, the sense of scale up can be to increase the flow rate. So as long as the power delivery is enough to catch up the speed for effective discharge of the electric discharge happening in water, we will be able to deliver more power and more mass, of air and water just for that, nitrogen fixation process or conversion to nitrates. So that's, of course, if like with one reactor, if we want even more ability or capability, we could do series connection of multiple reactors or in parallel connection. So that's also a different sense of scale up of this technology.
Okay. Another question that came in is the fertilizer liquid or solid, and what are the production rates?
So now we are producing a liquid fertilizer because we are fixing the nitrogen in the air into water and directly in water, like the discharge and the fixation process happening directly in water. So it makes more efficient than you discharging air and you purge the air or into water. Then that's like you lose some of the reactive species or nitrates or nitrite species produced on site. So what our technology, the advantage of our technology is to discharge directly in water, and the mass transfer is a lot improved. So yeah, to answer your question, the fertilizer is liquid. So just depending on what level of concentration we need. So we can control the different process parameter to achieve the certain concentration you want. So that's our goal for the next step to, yeah, optimize the process.
Okay.
So what are the production rates? So right now, yeah, that's still, that depends on how much of concentration you want. So if, so in this preliminary data, we used, for example, probably half an hour, you can produce 2 liters of 300 mils per minute, 300 milligram per liter of product. That kind of scale for now.
Okay. All right. Well, it looks like that's all the questions that have come in. Thank you for that presentation and being with us, answering questions and answers live. Okay, we're going to now move on to the last presentation today, which is going to talk about multi-stage membrane systems for nutrient recovery. So,
hi everyone, this is Zahra Anari. I'm going to talk about our project, multi-stage membrane configuration for nutrient recovery as fertilizer. This project is funded by Mass Center, NSF Industry University Cooperative Research Center, and the supervisor, my supervisor is Dr. Lauren Greenlee, and co-PI for this project is Dr. Greg Thoma. The take-home message for this study is that membranes can be used not just for contaminant removal, but for nutrient concentration and recovery. The motivation for this project comes from the fact that by concentrating nutrients in the wastewater, we can have higher efficiency of street-wide precipitation. So the previous studies in Greenlee Research Group shows that higher concentration of nutrients would yield in greater recovery of street-wide in an electrochemical street-wide precipitation reactor. So by precipitating nutrients, we can have higher efficiency of fertilizer precipitation. Also, another reason is that nutrients can precipitate in as unwanted precipitates in the wastewater treatment plants equipment, and by early removal of these nutrients from water, we can prevent this falling and decrease the maintenance cost. Also, we can, by this way, we can meet the wastewater discharge limits. So the goal here is that to pre-concentrate the wastewater, nutrients in the wastewater, and then use it in the electrochemical storage reactor, or just concentrate nutrients and directly use them as organic liquid fertilizer. So we are studying membranes, pressure-driven membranes here to pre-concentrate nutrients in the wastewater. So the goal here is to investigate the effect of membrane polymer chemistry and pore size on nutrient recovery, and also screen the procedure by life cycle assessment to decrease the environmental impacts of the process. The objectives is to obtain a set of commercial membranes to evaluate the performance and conduct cross-flow filtration experiment and LCA analysis. Also conduct real wastewater experiments for monitoring the nutrient recovery. So I will go through the concept of nanofiltration very short. So the removal is dependent on both source exclusion and Donan exclusion. Donan exclusion is repulsion by charge. So if the surface of the membrane is charged, it will repulse the membrane with the same charge, the ion with the same charge. Also, if the pore size is small, it will exclude the ions by size. So most of the nanofiltration membranes are negatively charged. Their surface can repulse most of the anions. But in terms of ammonia, since it's a cation and it's a very small ion, it's hard to reject it unless it's a very low pore size membrane, like fine pore size nanofiltration membranes or reverse osmosis membrane. Here is the schematic setup of our nanofiltration module and nanofiltration Karlsruhe filtration system that we use in this study on the left side. So on the very left, we can see that there's a feed tank. The wastewater is kept in there and it is recirculated through the system by a pump and through the membrane module. Pressure is applied on the membrane and a portion of wastewater is pushed through the membrane. And by this way, nutrients are rejected and are staying on the feed side. So we are dewatering the wastewater and keep concentrating the nutrients on the feed side. At the final stage, the concentrated nutrients can be either directly used as liquid nitrogen fertilizer or be sent to electrochemical Struweit reactor to precipitate them as fertilizer. So we provided 7 different membranes, 6 nanofiltration membranes from very low pore size to large pore size, and 1 RO membrane with a very, since RO membrane is a very, has a very low pore size and it can be effective for nitrogen removal. We have polyamide thin film composite among our membranes with different pore sizes. We have cellulose acetate, we have polyether sulfone. Preliminary results, but with filtering synthetic wastewater, including nitrogen and phosphorus with an NP ratio of 10, we found out that polyamide thin film composite, they have better removal, mostly because they are more charged on the surface, and they can all remove phosphorus very good because phosphorus is a large ion, also it's a negative ion, but some of them with the very low pore size, they could remove nitrogen more effectively compared to the larger pore sizes. We down selected these 4 membranes to test them in a longer term filtration and with synthetic wastewater simulating poultry wastewater or with real wastewater. So if you look at the FTIR spectra of these selected membranes, they are all polyamides with similar peaks, but there is a slight difference on the surface of these membranes. So RO and 400 Dalton TFC membranes, they are fully aromatic polyamides, which makes them to have a rougher surface, which we will show in the next slides. And 250 Dalton and 300 Dalton TFC membranes, they are semi-aromatic membranes, which makes them to be more hydrophilic compared to fully aromatics and have higher permeation rates. So we tested these 4 membranes with filtering synthetic wastewater simulating Tyson poultry wastewater in 10 hours filtration. We tested all of the nanofiltration membranes at 5 bar. We considered 2 conditions for RO membrane. The realistic condition for RO is 20 bar, but we also added a 5 bar to be able to compare the performance to nanofiltration membranes. We can see that 300 Dalton TFC membranes has the highest phosphorus concentration factor because this membrane had a high phosphorus removal, same as all the membranes. They have a very good phosphorus removal, but this membrane, since it's a semi-aromatic membrane and it has a more hydrophilic surface, it could have a have the highest flux and permeation rate among the membranes. So it could concentrate the phosphorus much better than the others. But since it had a low nitrogen removal rate, it couldn't really concentrate the nitrogen because most of it was passing through the membrane. Between 250 Dalton and 400 Dalton TFC membrane, they have similar nitrogen recovery. Although 400 Dalton has higher removal rate, but slowly higher removal rate. But since it had a higher flux decline, which we will show in the next slides, it could pass less water through the membrane. So the water, at the end, the concentration factor of these two membranes were similar. RO membrane at 20 bar definitely had a good concentration factor, but if we want to stay in the low range energy consumption, RO membrane, since it has a very dense top layer, it's not a good option for concentrating these nutrients compared to nanofiltration. So the SCM of these membranes shows that used RO membrane and 400 Dalton TFC membrane has more fouling on the surface compared to the semi-aromatic membranes. It's because fully aromatic polyamides have a rougher surface that can trap more species. In the next slide, we will talk about it. The flux decline also for these fully aromatic membranes is higher, but semi-aromatics have barely flux decline during the process. So as I said, fully aromatics, they are more rough on the surface. Their structure is called region valley. So if you look at the green dots on the pristine membranes of RO and 400 TFC, we can see that the green dots are more filled out on the used one. It shows that the valleys are clogged by species and by contaminants during the filtration. It's easier to be fouled compared to semi-aromatic, which has a less rough surface and more hydrophilic surface. So the flux decline is higher for these types of membranes. But also the rougher surface would help them to have a more selective, more selectivity toward nutrients. So there is a trade-off. So the next step was to test the real wastewater with our membranes. So the purpose here, the target here considered to be ammonia concentration. We wanted to have a very highly concentrated liquid nitrogen stream at the end. So we chose a single step nanofiltration just to concentrate nitrogen. We pre-treated the wastewater prior to sending it to the nanofiltration system to take out all the suspended solids. We chose 250 Dalton and 400 Dalton TFC membrane to test for nitrogen recovery. It shows that at the final stage, we have higher concentration factor with 250, have a higher concentration of ammonia at 250, with 250 TFC membrane. And since it has a more flux and permeation rate besides the good nitrogen removal rate. So it's a promising membrane for hitting 2 to 4% concentration. And we will test it with a larger module to have higher capacity of wastewater, to test higher capacity of wastewater. And we analyzed the performances with life cycle assessment. We considered that if we have a multi-stage membrane configuration to have 2-step or 3-step of removing nitrogen and phosphorus in separate steps, and then combining them, combining the concentrates for street-wide recovery, and also the third option, removing nitrogen, the excess of nitrogen for organic nitrogen fertilizer recovery. We found out that environmental impacts are not dependent on membranes. They are mostly dependent on the configuration. So multi-stage membrane configuration would have higher environmental impacts compared to single step. There is no significant difference for street-wide recovery between the membranes, because the P removal is similar, and P is the limiting factor in street-wide precipitation. So basically, the membrane selection is not really affecting the environmental impacts, and it's the configuration that it has a major difference in terms of the environmental impact. So the conclusion here is that polyamide thin film composites are appropriate options for nutrients recovery. The slight difference on their surface has a huge impact on performance and the type of nutrient that they can recover. Polyamide thin film composite with a pore size of 250 Dalton is promising for ammonia concentration as liquid nitrogen fertilizer, and the environmental impacts are not dependent on the membrane selection, but dependent on the configuration. At the end, I would like to acknowledge Mass Center, Tyson Foods, and Garver companies for funding this project, and University of Arkansas for facilitating this project. Thanks for listening. I would be happy to answer your questions.
Okay, so we will now take questions. Our last speaker today. There are a couple questions came in. First one is, what are the pre-treatment requirements for this technology?
That's a great question. So the answer would be, we need to use an ultrafiltration prior to nanofiltration or reverse osmosis to remove all the suspended solids, the particles that are not in the solution and are suspended. We need to take them out. Other than that, I think we can use the raw wastewater, pre-treating it with ultrafiltration, then send it to the nanofiltration system.
So it's going to need to be a pretty clean stream of material there that before it goes through this treatment technology then.
Right, we are currently using a stainless steel ultrafiltration membrane that can be, like, all the system is stainless steel. It can be, if there is a huge concentration of suspended solids in the wastewater, it will fall the membrane, but since the membrane is stainless steel in the pre-treatment system, it can be washed with high pH solutions or very low pH solutions to it can be strongly washed with clean solutions. And we are actually in another project. We applied, the University of Arkansas actually applied and tested the pre-treatment system on the raw wastewater of the Tyson poultry wastewater for removing all the suspended solids.
Okay. All right. And then the second part of that, and maybe you've answered already, but as an example, would you need to use reverse osmosis first before you use this other membrane technology?
So the reverse osmosis, since it's very sensitive to the fouling, it has to be the last step prior than that. So you would have to lower the pore sizes step by step. So it has to be first ultrafiltration, then nanofiltration or reverse osmosis.
Okay. Well, it looks like that's the last of the questions that have come through. So again, I'd like to thank you for being with us today. So for those of you that are left on, we've got a 3-question survey. Would really appreciate you taking a moment to answer that. And then after that survey is completed, I'll pop up the QR code for those of you who want CEU credits. So I'm going to stop the recording at this point.